Hi, Chris. This is Penny. Would you like to get started? And we talked earlier that maybe we'd have the people, as you introduce us, put our webcams on.
Yeah, I'll give a brief introduction, and then that'll include giving an introduction to our presenters today.
Awesome.
So we'll go ahead and get started. We've got a lot we're trying to cover today, so we're going to try to keep things moving along. As Penny said earlier, we're trying to reserve some time at the end for a larger question and answer period, and if it allows, we'll have some question and answer quick sessions between presenters. But if you have anything that pops up that you want to ask, please put it in the chat. We'll be saving it in a larger document to hopefully address at the end and throughout. And then if we need to, we can address some bigger questions through email after the event. So I want to thank you all for joining us today for our Fish Passage, Flood Resiliency, and Road Stream Crossings virtual workshop. We love to do these events in persons, but after the past year, obviously we just wanted to keep conversations going and keep making connections and new partnerships. So we've been blown away by the response to this workshop, and thank you all for joining today. Just kind of a brief overview of why we're here. Road stream crossings are a major part of our communities and infrastructure, and when they don't perform, we see severe impacts to the natural environment and stream health and to community safety. That's largely due to past practices that resulted in road stream crossings that either aren't installed properly or are undersized, and that results in an oversized impact, ranging from preventing fish like brook trout, pike, and sturgeon from being able to reach spawning grounds and other important habitats, to just not being able to pass flood flows, which are becoming more frequent and more hazardous, resulting in roads that fail, crossings that wash out, cutting communities off from emergency services, and just making travel less safe. So what we hope to accomplish today is, like I said, we're covering a lot of information, and we're not trying to leave today with you all being experts on everything road stream crossings. What we're looking for is to start a conversation, to show you some tools that are out there, to introduce some partners and funding ideas and practices that you can use in day-to-day road stream crossing management, to start looking at managing our road stream crossings differently, to benefit both the natural environment and our communities. So just a brief overview of what we're covering today. First up is going to be Dale Higgins. Dale is retired from the U.S. Forest Service and has done a lot of work across northern Wisconsin in the National Forest on road stream crossing work, working with a design method called stream simulation design, which works to create culverts that both perform better for human use and protecting our communities during higher flows and floods, but also to improve aquatic habitat and just resource management along our streams. Then we're going to have a conversation on permitting and construction tips and best practices. That'll be led by Maureen Millman and Bobby Joe Fisher from the Wisconsin DNR. Then John Simonson from the Wisconsin DNR is going to be giving us a presentation on why we complete road stream crossing inventories and how those are useful to managers and your partners. And then I'll be closing out our sessions with a discussion on partnerships and funding opportunities that'll largely focus on roles Trout Unlimited's been filling in our partnerships, but also give a broader overview of what partners across the region and even beyond can do. A lot of these topics are based on examples from Wisconsin, especially northern Wisconsin, but most of the stuff is applicable on a very broad scale, if not more specifically across the Great Lakes Basin and the broader upper Midwest, and honestly across the country. So there's a lot of tools we'll be talking about using Wisconsin examples that even if it doesn't fit your streams you work with, it's something you can take some information from and apply it in your region. And then we're going to close with a wrap up question and answer period. And without further ado, I will stop talking for the time being and turn it over to Dale to get this started.
Okay, I'll go ahead and get started. As Chris said, my topic's ecological culvert design for fish passage and flood resiliency. And I'd like to start out with a little story. Okay. There we go. Sorry about that. So Chris mentioned I'm retired, but I worked for 38 years for the Forest Service. And the last 30 of those on the Chequamegon-Nicolet National Forest, northern Wisconsin. And my whole career worked on road stream crossing problems, but especially those last 20 years, spent a good share of time on those problems in northern Wisconsin in particular. And so over that 20-year period, probably 7 or 8 years into that, we were replacing roughly 12, 13 crossings a year. I thought we were doing a fantastic job. It was a lot of work, kind of getting ready to pat myself on the back. And then I did a very simple math calculation. I knew we had roughly 1,000 stream crossings, maybe more of that on the forest. So I took that divided by 12 and a half, and I came up with 80 years. So, it struck me that our structures need to last 75 to 100 years at that rate. So, the point is that I'm getting quite a bit of feedback, thanks. So the point is that any structures we put in the ground today, just from an infrastructure standpoint, need to last at least 75 to 100 years. So you got to think immediately about lifespan, and they have to be flood resilient. So, and if you look at the diagram on the left here, this is something I got from Mike Miller, and I think it's actually from southern Wisconsin, but the red dots are secondary roads. And then some of the other lighter colors are more freeways, main highways. But, the bottom line is there are a lot of stream crossings out there. So, so many crossings, so little time, so little money. So when we replace a crossing, we got to do it right, because we're going to live with it for a long time. So here's kind of the overview of what I hope to cover today. And Chris mentioned that we're really just going to kind of give an overview on everything, touch on all these topics briefly, just a little bit on the biology side of things, fish and aquatic organism passage. You'll hear the term ALP, a little bit on stream geomorphology. And I want to cover that because it turns out that if you account for the stream geomorphology, you can make a much more flood resilient structure. Touch a little bit on hydraulics, hydrology, traditional, what I'm going to call traditional culvert design, so we can contrast that with what I'm calling either stream simulation or ecological culvert design. We'll go into a little more detail on some design concepts for those two topics. Touch on some of the flood resiliency aspects, and then just at the very end, no economist to touch a little bit on costs. So I'll go ahead and get started. Just talk a little bit about fish and aquatic organism passage. A few of these slides I borrowed a while back from Mike Miller with DNR. And the point is that species, whether it's fish or other species, they have a variety of needs to meet their life cycles. And rarely are all those habitat needs provided in one place. So they gotta move to get to them. And of course, that certainly applies to fish, aquatic organisms. And road stream crossings frequently become barriers, can become barriers for movement. Example here of traditional culvert design gave us a lot of these types of structures with the jump, with a barrier jump at the outlet where species might have to jump that. Even if they can make the jump, the water in the culvert might be too shallow for them to swim through or too fast. So, the classic example of, species maybe requiring to move are brook trout or other trout, game species that, either need to seek out spawning grounds or colder water temperature or overwintering areas. But I'd like to, if you're not aware of some of these, broaden your horizons a little bit. A lot of people don't think about intermittent streams maybe as being important for aquatic organism passage. But here's an example. This is just a roadside ditch, drains into Lake Michigan and Lake in Green Bay, and only carries water for up to 2 months per year in the spring. But guess what? Northern pike, the ditch runs into the lake. Northern pike spawn up, move up ditches like these. They get into wetlands and flooded fields. They spawn. Eggs hatch in 12, 14 days. And then in 3 to 4 weeks, the young migrate out. Within a month, the ditch is dry for maybe 10 months out of the year. So plays an important travel route for northern pike, not only out of Lake Michigan, but maybe this is probably happening everywhere. So another perspective, this is an example from down southwestern part of the state, near Platteville. We were down there working on sites for a road stream crossing workshop. This is November of 2015, and there was a box culvert with a 1 foot drop. And to my way of thinking, I always thought if anything in late fall, early winter, fish migrate downstream to find overwintering areas. So here it is, November, and we saw dozens of little fish attempting to jump this 1 foot drop. We couldn't identify them. Here's one right here. It's another one over here, and they would jump up and fall back, jump up. So here are these small, minnows trying to migrate upstream late in the fall. So that sort of the take-home story is that we know a lot about fish and fish movement, but we don't know everything. We keep learning more. But species really determine when they want to move and in what direction they want to move. So I always feel like, from my perspective, we should provide them the opportunity to move when they want to move. So, and the same thing applies maybe to turtles. They need to move if they can't get up through a culvert and they get forced up over the road, especially areas where you have high traffic, they can become killing fields. Species you don't think about moving are mussels. They're pretty sedentary, but they actually in their life history expel something called glycidia, which attach to the gills of fish, and then the fish can move upstream. Eventually they'll drop off and mature into adult mussels. So a whole variety of species move. Even there have been some examples of mayflies, amphipods, snails moving upstream. So the bottom line is, I think I already mentioned, I think the best way to look at it is provide them the opportunity to move when you can, and let them decide when and what direction they're going to move. And I don't want to go back to that first slide I showed where I talked about the need for, just from an infrastructure standpoint, for structures to last 75 to 100 years. If we put in structure today, it's going to be out there for another 7,500 years, and we don't get the aquatic organism passage side of it right. Those critters in that stream at that site are going to live with those consequences for a long period of time. Okay, so next I want to move on to stream geomorphology, and there's some important concepts I think we need to consider and provide background for later in the presentation. So I want to start like at the big scale and just kind of very simply, talk about the fact that stream networks develop in watersheds in response to geology and climate. Geology is kind of the template that stream network develops in. Climate provides the water, which produces runoff, runs downhill, right? But not only does water runoff inform channels, so does the sediment, moves sediment. So the combination of that water and sediment runoff works to form stream channels and floodplains. So, just a simple overview. So if we step down to the stream level, again, I want to emphasize the importance of streams not only moving water, but sediment and even wood and organic matter and that sort of thing. And so doing that, they form and maintain stable features. You'll hear the terms dimensions, patterns, and profiles. Dimensions would be, say, if you look at a stream in cross section, the width and depth of the stream, width and depth, maybe the width and depth of the floodplain. Pattern would be sort of the plan view of a stream. Is it very sinuous, or is it straight? Does it have very narrow floodplain? And then the profile would be the slope. Here you see sort of a classic pool, short riffle, pool, short riffle. And so you can look at all these features and you can measure those, and people have used these to classify and characterize streams. So the bottom line is, though, that streams develop these characteristics and they sort of maintain them over time through scour. So that there's your sort of hydraulics and flow, but also deposition, movement deposition of sediment. So key feature, a lot of you are probably familiar with this, have no doubt heard it, but the term bank full flow and bank full channel characteristics. And that's a key concept I'm going to use in ecological design. So what are we talking about in terms of bank full flow? And it's probably the flow that is most important in forming and maintaining the channel. And it tends to carry the most sediment over time. And it has a fairly consistent return interval, if you're thinking in terms of flood frequency, about 1.5 years, although it can vary from maybe just over 1.1 up to 2 maybe, but 1.5 good average. And here's an example of what we're talking about. And it's defined as just filling the channel before it flows over in the floodplain. So if you can see the flags in this example here, there would be your bank full channel. So we're at low flow. And usually one good place to see it is on a point where you come up and then it flattens out onto the floodplain. So here are the streams just about at bank full flow. So Couple other examples of how to identify bank full. It's that first depositional flat adjacent to the main channel where the stream will start to flood out. So here's an upland, I'd call it an upland situation. So you come up this bank and all of a sudden there's a break right along here and you'll have this flat. So that would be the floodplain. This would be your bank full elevation, or at least the first point you would look at. Throughout the Midwest, northern Wisconsin, the entire Midwest, lots of streams located in wetlands. So here's a classic example of that where you have wetland, sedge hummocks, low gradient stream, pretty steep vertical bank right up to this point. And that's a field notebook lane there. So that's a flat actually. And you can pull the sedges back and look at it. So that would be the bank full channel in a wetland area. Thing when you're doing that, you just want to be careful about avoiding the hummocks. These sedges can have hummocks and they'll stick up higher. And then also sometimes you get some natural sand, discontinuous sand levees that might develop out here, and you want to avoid those. So diagram of what that looks like in cross section. So here's your bank full stage and bank full width, channel width, flat adjacent to it. So this is a floodplain. You can calculate a average bank full depth, area, also maximum depth. And if you're familiar with Rosgen's stream classification system, you'll hear the terms too: flood prone width and entrenchment. So flood prone width is, he just rule of thumb, take the maximum bank full depth, double it, extend a line across where that intersects with the uplands. That's the flood prone width. And then he'll use the value, and a lot of other people do, of entrenchment, which is just this flood prone width divided by the bank full width. So it's how wide is the floodplain in terms of bank full width. So in this case, it's probably about 2. If these uplands came in here, it'd be an entrenched stream with a value of less than 1.5. If it's out beyond about 2.2, you would call that slightly entrenched, so you have a broader floodplain. So it's an important thing to think about when you look at your road stream crossing, well, what kind of entrenchment do you have there? Do you have a very entrenched, narrow floodplain, medium, or a much broader floodplain? So the last thing I want to touch on here with regard to stream geomorphology is this little scale here in diagram referred to as the lane diagram. And it helps you think about how streams balance out sediment load and discharge, and what can happen in terms of the equilibrium of the stream. With regard to road stream crossing, you can look at this diagram and say, for example, some existing crossings, the culverts had high strips to channel, so ponds water back upstream, or at least during high flows. So that has the effect of decreasing the slope. So you could move this in, what's going to happen, then this will drop down and you're going to cause aggradation. Of course, that's exactly what you see upstream from some of these crossings. You start to see, depending on the slope of the stream and the sediments moving, gravel, sands, or organic matter grading upstream. We've had a number of crossings that failed frequently. And so part of that is you increase the sediment load downstream, this drops, again, aggradation, but downstream. Even if some of the fines wash away, you're left with more coarse material, maybe from the road fill. That's like sliding this out, again, aggradation. And I have an example later on where you might change the slope and that can lead to degradation. So enough on channel geomorphology, just quick background. Want to touch on some culvert hydraulics to make sure we all have a common understanding of a few terms. And I want to start here with this diagram. Here's the culvert, road prism, water, the stream is flowing from left to right. So the invert of the culvert is bottom of the culvert, right? The headwater is the depth of water here acting on the culvert, a little back from the straw down. The tailwater is depth of water below the culvert, influencing flow through the culvert. The critical parameter I want to make you aware of is something called the headwater to depth ratio, or pipe diameter if it's a circular pipe. And that's merely the headwater depth here divided by the depth of the pipe. So it's just a ratio. So in this case, you're at about 80% of the height of the pipe. So headwater to depth ratio of about 0.8. If you're designing a culvert and you said, I just don't want it to overtop the road, in this case, you would say we want to pass our design flow at a headwater to depth ratio of 1.9, which, and you can see so not only is the flood frequency important, are you going to design for a 25, 50, 100-year flood, but at what headwater to depth ratio? And for ecological culvert design, we're actually going to recommend less than this 0.8. So, and I'll hammer that into you over time. So a couple other quick things: supercritical flow, you'll hear that term. Think of it as shallow, high velocity, subcritical, deep solar water. So a few other things in terms of culvert hydraulics, you hear the term inlet control. That means that the only thing determining flow through the culvert is the headwater elevation here, and then the inlet characteristics. Flow in the culvert's can be supercritical. Usually the culvert is set at a steep slope. So, and means the culvert barrel itself can convey more water than you can get into the inlet. So if you're thinking about pressure on your road crossing, if you're thinking about abrasion in the pipe, fish passage, supercritical flow is a problem. So outlet control, kind of the opposite. The tailwater really determines the flow through, along with a number of other characteristics. So flow through the culverts can be subcritical, and means that the inlet can convey more water than is flowing through the barrel. So this is certainly the type of thing we'd like to see for aquatic organism passage. A couple notes on hydraulic analysis. Don't have time to go into that in much detail, but this picture of this book here, Hydraulic Design of Highway Culverts, Hydraulic Design Series 5, HDS 5. This is like the old Bible. I think it goes way back to like the 1950s or something. It's been updated several times, but that's what was used before the advent of computers and computer models. But a lot of this still forms the foundation for these computer models, and these are basically just computerized solutions using a lot of these techniques. There are a number of models available. And HDS 5 has, before today's computers, these nomographs you could use to help solve for either inlet or outlet control. And so a number of computer models. I'm going to just talk briefly about one, HEC-RAS. U.S. Army Corps of Engineers has a hydrologic engineering center. That's the HEC part. RAS is a software package called River Analysis System. They have a number of really good software packages in the public domain. So that's one that's commonly used. It's a floodplain modeling program, but it has really good routines for culverts and bridges. So that HDS 5, I mentioned they have these nomographs, and I'm going to show you a few just briefly for a couple of reasons. So here's headwater control. So it's kind of a quick and easy way to design pipe. If you let your with your headwater you can solve, and you have design discharge, you can identify a pipe. The thing is, I'm going to recommend you don't ever do that for designing a culvert or road stream crossing for a variety of reasons that I showed you already, and some I'll show later. But you could use this maybe as a quick and dirty way to design maybe a bypass pipe for a week or two. So that's one reason I show it. Another reason is here's kind of what the modules look like for HEC-RAS. So you need survey data. So you put those in, it's called geometry data. You need some kind of flood flows to model. And then you execute the program. And what the program will do is it will calculate at each cross section and at your structure depths and velocity. So the hydraulic side of things, see if you meet your standards. So as you're putting your geometry data in from your survey, you put in the elevations for culvert. You also have to pick your culvert size. And there's actually, as you're picking those, if you look, there are links back to these chart numbers, so you can make sure that the structure you use and fits quite well. So I think enough said about hydraulic analyses. So the next thing I want to do is go on and spend the next 10 minutes or 15 minutes so talking a little bit about hydrology. And of course, the reason for that is do successful ecological culvert design and construction. I'll throw construction there. You need the ability to estimate some flows, in particular flood flows, but maybe in some other cases, more typical range of flows, especially like for bypass pumping or something. So just a little bit of background work. There are two basic ways to estimate discharge at your road stream crossing site or any other site. one broad category would fall into what I'd call rainfall runoff modeling. So that's where you pick a design storm, a rainstorm, which could be a 25, 50, 100-year event. And then you also, with rainfall, though, you got to think about, well, what duration? Is it a 6-hour rainstorm, 12, 24, et cetera? And then you can get a design rainfall amount. Well, you get in essence, drop that on a watershed, figure out how much is going to run off, and you can get a peak discharge from that and even a runoff volume, and then you model that, size it. So and there are some really good methods, and so it's a reasonable way to go about it for doing that. But the one drawback to me is that it doesn't take into account snow melt. It doesn't take into account necessarily, 2 or 3 or 4 or 5 days in a row of 2 to 5, year storms. So the other approach you can use, which I like to use, and I'll talk about, is basically transferring data from streamflow gauging stations, because that's really what you're interested in, are observed flood flows. And so I'll get into that in a lot more detail. So that's all. I'm not going to say anything about rainfall runoff modeling. I'll cover this aspect today. So since I'm talking about gauging stations, there are 2 basic types: continuous recording, and then something called partial crest record. And then there are sort of 2 basic types of data. And the most important one for flood frequency analyses are the instantaneous annual peaks. That's the absolute highest peak discharge at a moment in the year. So you have 1 per year. And then you can get those from both continuous recording and crest gauge sites. If you want more the normal range of flows, a lot of that continuous recording will provide that data. And usually they're recording every 15 minutes or something, but then they'll summarize that by average daily flows most commonly. We might use that for some other things. So, okay, so why annual flood peaks? What's our interest there? Well, I think it's pretty obvious. The main reason is we want to check the peak flow capacity of our structure. I think I already mentioned earlier that, in this course, I'm going to recommend the 100-year flood at a minimum with a headwater depth ratio less than 0.8, but you can consider checking up to the 500-year flood. But you also might need a range of other flood flows if for some ecological culvert designs you might want to do a bed mobility stability analysis. And so you need a whole range of flood flows for that. And then also, I mentioned under the stream geomorphology part that the typical bankful flow is about a 1.5-year flood. So if you have that estimate too, you can use that a couple of ways. One, you can use it to help verify bankful or where to look if you're not sure. Or if you have a really good bankful, then you can use that, model it, and see how well your modeling is doing. So it's kind of a quality control check. And a word about flood frequency terms. I'm using what I think most people use terminology, which you would call a recurrence interval, return period, average return period, 100-year flood, 50-year flood. And so the idea there is that on average, it would only occur once every 100 years, but that's not really the way it works. I just like to remind everyone, point out that the true way to think about the probability of extreme events or floods is the exceedance probability. So it would be 0.01, or that would be 1%. So a flood that has a 1% chance of occurring in any given year would be called a 100-year flood. But it certainly has that chance every single year, not just once in 100 years. So it's good to keep that in mind. Okay, so we may or may not need average daily flows, but the one area you might use them, and I have a quick example of that is if you're thinking about construction and what kind of bypass flows we may have, and we'll make sure we can accommodate that with either pumping or a diversion pipe or diversion channel, that sort of thing. If you want to do any kind of like fish passage modeling, we won't spend any time on this, but later on, John Simonson's going to be talking about inventory, and maybe if you have an inventory and one of your concerns is fish passage, some it's obvious whether you have or don't have, but some are indeterminate. You can do some modeling to determine that, and you need to pick out flows to do that. So how do you transfer flood flows from USGS gauges to your site? Sounds like a lot of work. The good news is the U.S. Geological Survey, who operates all the gauging stations in the country, they've done the vast majority of the work for us already. So at every one of their sites, once they have sufficient number of years of data, they'll do a statistical analysis of that site, flood frequency analysis, so they identify what the 2, 5, 10, up to 100-year flood is. And then, well, how do you extrapolate that? So then they develop methods for doing that too. They delineate every one of those watersheds, and they determine a number of watershed and climatic characteristics for that watershed. And then they perform a regression analysis, statistical analysis, to be able to predict the flood flows from those climatic watershed variables, and they're regionalized by state. And so they've done all that for us. So it really simplifies our job. In addition, that they've developed a little computer program that solves the equations, and it contains all the equations for a state. It's called NSS, and you can download it from right here. So, and the other thing is that as they do these analyses and develop these equations, they do it state by state typically. And then as they update the equations, this is from Wisconsin 1983, they describe all the gauges in the state, they describe their statistical analysis, the whole works, everything is here. So if you're going to use these regression equations, it pays to get these publications, look it over and make sure you understand it, understand the limitations, all the assumptions, that sort of thing. Again, from this website, you can download the publication. So here's an example. This is still from 2003. Map of the state. The open circles are those partial record crest gauge stations. There are a lot more of those because they're cheaper to operate. But then there's some continuous recording. And then again, you'll notice that the state's broken up into regions. There are 5 regions. And they do that because by regionalizing, they can get better regression fits. So they'll have separate sets of equations for each one of these regions. So one of the things that's nice about this approach is a statistical approach. One, you can plot these up. This is an example for Brookside Creek and Brookside Road over near Green Bay. You can plot them up, but because it's a statistical analysis, they also publish the standard errors. And so you can even plot those, and it gives you some sense of the potential error in your estimates for your flood flows. So the caution here is, beware of those standard errors and the possible error you might have in your prediction. I mentioned I like these regression equations. I think they have the potential to be a lot closer to true value compared to rainfall runoff modeling, but you still can have fairly substantial errors. And then the other thing is you want to be real careful because in those publications, they'll state the range of data used to develop the equations, and your watershed may be outside that range, and the potential for error goes up. One last note, a lot of them, like Wisconsin, starts at the 2-year flood down here. I like that 1.5-year flood. So I just simply, extend this line down to get the 1.5-year floods. Quick and dirty way to do that. So how do you go about using regression equations? Pretty simple, straightforward. You delineate the drainage area, you determine the watershed characteristics, you solve the regression equations. And in the old days, you'd have to get GIS layers, delineate the watershed, and then from there overlay it with the watershed characteristics you need for the regression equation. And then you could either solve it with a spreadsheet equations or this NSS program. USGS is making our work even a lot easier. They have a program now called Stream Stats. It's a web-based watershed delineation program. You can go into here, move into your state, you zoom into your site of interest, click it, it'll delineate the watershed, then it'll bring up the layers you need to solve your equations. And so it'll provide all the data you need. Some states will even solve the equations. Wisconsin's not there yet, so you still have to either use this NSS program on your desktop or a spreadsheet, something like that. But pretty simple, straightforward. Here's an example, that Brookside over by Green Bay, long, narrow watershed, delineated the old GIS, 3.9 square miles for the regression equations for that part of the state. You need storage, channel slope, soil permeability, mean snowfall. You get that either off the maps or from the publication. This is just an example of what a few of the equations look like. Like I said, every area has its own set. They'll have it for the Q2 through the Q100. And so area, storage, slope, soil permeability, snow. For that particular site, the solution. 100-year flood was 380 CFS. And you can see the other numbers here. One thing I like to do, and it's a little crude, there are a few things you still got to take into account, but I'll divide that by the drainage area, come up with almost 100 CFS per square mile. So as I move around areas of the state, I get some ideas. Is it a flashier, more stable system? And I have some other examples like that for you to see and think about. So so the next thing I want to do, hydrology. You may or may not want to do this, but it's something else to think about, and it gives you a feel for the hydrology system. So say you want to think about bypass flows during construction. So, you know, the thing to do is the obvious thing, well, when will construction occur? Do we know? Because flows are seasonal. Determine the length of construction. Can you get in a day or two, or is it going to be a month-long job? And then you can kind of figure out, like using average daily flows, what a typical or upper flow might be, and then you can prepare for that or start to size for that. It's going to be a long period of time. You might want to use like a 2-year flood or something, and then you can from that size your pump or diversion. So, well, how do you go about doing that? Well, one way is you can use that gauging station data. Again, it's real easy to access, download, or you know, if you got a hydrologist or someone like an engineer, maybe can do that for you, or maybe they've done it already. So here's kind of example working in northern Wisconsin. I've taken a lot of the gauges and generalized them, but here are individual gauges. So and the thing I want to point out here is you can kind of classify these gauges and into different flow regimes. And so the other thing I did is, so if two watersheds have exactly the same characteristics, climate, but one is twice as big, the flows are going to be twice high, right? So all the flows from these 4 sites are divided by their drainage area. So it takes that out of the equation. So what you're looking at are differences in watershed characteristics, how they influence runoff, maybe a little bit climate if they vary around the state. So like in northern Wisconsin, this blue line reflects a very heavily groundwater system. Doesn't move too much, very high base flows. The red line is more of a surface runoff dominated watershed, very responsive rainfall, snow melt, higher peaks, low flows. And then the purple line is kind of in between, something you might call mixed. It's kind of in between the two. So over, the one example I have is over by Green Bay, so that I was just showing you. So well, what does that look like? And here's a gauge, and it might kind of mimic this. So similar to the mixed, except that it peaks a little lower, or it's about the same, but a little earlier, which makes sense, a little further south, maybe, and then the base flows are a little bit lower. So you can use this to get an idea of this year construction period, and you can kind of get an idea what the flows are per square mile, multiply that by your drainage area, and it gives you a starting point. So here's an example that generalized a little more monthly flows, but then averaging a number of groundwater fed systems or mixed or surface or 4 gauges in the Green Bay area. So for that Brookside example, say our construction was going to be, we knew it was going to be in July. If it was later, you might even have lower flows on average. So at a minimum, we'd want to be able to handle that flow about 1/4 of a CFS per square mile times almost 4 square miles. So it's a good starting point, almost 1 CFS. So or if you wanted to pump, say it's a small system, you can get in and out in a few days. Maybe you need a pump that would do at least that and more reserve capacity in case flows are higher at that time of year. And certainly as the construction time approaches, then you can adapt accordingly, but it gives you a starting point. Another example here, say you're going to be in there for 3 weeks or a month pouring concrete and other things, and you think there's a good chance that you could have some storms and some higher runoff rather than the sort of average or base flows. So then maybe use from irrigation equations a 2-year flood, in this case 135. So we'll say you're going to put in a diversion pipe and you can set it steep and you're willing to, you're only going to be in there a few weeks. You're not too worried about fish passage or abrasion, that sort of thing. So using your survey data and then those nomographs, you could specify inverts, the culvert up and down. And then you also can think about how high do our cofferdams have to be so they don't overtop at this flow. And then you can use those nomographs, headwater depth ratio 135. So it gives you a quick and dirty start at maybe sizing a diversion pipe. You can also do some of this in HECRAS, but it takes a little bit more work. So it just depends on how much time and effort you want to do. But At least it gives you a starting point anyway. So now the next thing I'll do is talk briefly about what I'll call traditional culvert design. And, that's essentially based on hydrology and hydraulics, select a design peak discharge. And of course, you got to think about what headwater depth ratio. And you get a survey, you perform some type of hydraulic modeling to pass that design discharge, ensure you meet your engineering constraints. So this is pretty typical of what we've seen with a lot of traditional culvert design. Culverts a lot narrower than channel width. You get this big plunge pool at the outlet, sometimes a drop, because you're constricting the channel, building up a high headwater during high flows. So the other thing though I want to mention is this idea of not only design standards, but the importance of headwater to depth ratio. So here are just some examples. These are minimum standards, so they can go beyond this, but Federal Highway Administration, 50 or 25-year flood with a headwater to depth ratio either less than 1.5 or 1.2, depending on the road type and the size of the culvert. Wisconsin, pretty similar, 25 or 50 for streams, a little bit depending on the road type, but headwater depth ratio less than 1.5. So letting a pretty good head build up on the structure. And then NRCS, Natural Resource Conservation Service, they're working with private landowners, farmers, yikes, 2, 10, and 25-year flood for forest access roads, farm driveways, public campgrounds. So, what's the upshot of all that is tends to disrupt channel continuity. So, this H&H traditionally has been used really to minimize culvert size and construction or installation costs. So meet that minimum standard, put in the smallest pipe possible. And, a lot of us call that squeezing as much clear water through the pipe as possible. So why not just water? Why clear water? Because it doesn't take into account those geomorphic considerations I talked about earlier, especially things like sediment transport, the profile of bank fault characteristics. So anyway, traditionally what the H&H design has done is it results in these high headwaters, upstream deposition of sediments, high velocities through the culvert, which disrupts aquatic organism passage, leads to culvert abrasion, downstream scour, and also maintenance problems in terms of debris plugging and that sort of thing, and scour at the inlet, and definitely increased risk of failure. So that leads me to, what's a culvert designer to do, a road stream processing manager to do? And what I'm going to say is use ecological culvert design, also known as stream simulation. Or if you want a corollary to H&H, I would call it BGH&H, biology, geomorphology, hydrology, and hydraulics. So what's ecological culvert design? Simply structure width greater than equal to bankful width, structure wraps around natural channel, passes all aquatic species and life stages, maintains stream continuity in terms of the movement of water and sediment and even woody material. And that results in very long-lasting, flood resilient, low maintenance structure. So one of the things I'm doing, I've kind of broken this ecological culvert design into what I'll call moderate to high gradient streams, very low gradient. Classic stream simulation is like this: you build a stream bed through the structure, wrap structure around it. But at least in northern Wisconsin, kind of through trial and error and starting to work in this direction early on, we found that, well, maybe on these very low gradient streams, you don't always have to build bed and banks through it. So what are the key considerations to separate those two? Obviously gradient is one, but the key is that you have a natural backwater, tailwater, whatever turbulence through that backwater up through the culvert. The other key one is kind of what kind of a mobile bed do you have? You have a mobile gravel bed, not build the bed and banks through it. But if it's sand, organics moving through the end, you have this natural tailwater, you might be able to get by with what I'll call the very low gradient approach. Don't have exact slope breaks because it depends a lot on the details, especially the culvert length and the actual slope, but kind of very low gradient, you start getting below 0.5%, monitor high gradient above 1, and it depends on a lot of these details. So I think at that point, I'm going to stop for a break. We're about almost halfway through. I think we were going to take about a 10-minute break. So we'll do that now and I believe come back in 10 minutes. So
yeah, that's what we'll plan to do, Dale. We'll go ahead and take a 10-minute break for people to stretch, grab some more coffee or grab some breakfast. We'll plan to be back here at 9:25 and we'll pick up with Dale's second half to this session.
okay. See you in 10 minutes. The people I worked with over the years and learned from and that sort of thing. So I'd just like to give a shout out to everyone that helped me throughout the years. So I'll go ahead and get started. So next thing I want to do is step into just an overview of the design steps for ecological culvert design or stream simulation for these moderate to high gradient streams. You know, kind of the quick overview: culvert width greater than bank full width. You're going to build a natural channel through the road crossing, wrap structure around it. Well, how do you build that channel? What do you use? Well, you locate a reference reach nearby and you study the bank full width, the slope, and the bed material, and you use that as your template for building your channel. And then the idea is that that will pass all aquatic species and life stages, just like they do upstream or down in the channel. And also, you know, the sediment and water in like fashion. And then, you know, at the end, you do this hydraulic capacity check, sediment transport check, that sort of thing. So, okay. There we go. So, you know, do any design, you need to do a survey, right? But like from a stream simulation standpoint, we like to use the term site assessment. And you actually can do an initial site assessment before you even get on in the ground using existing information, maps, books, Google Earth. You can learn a lot in a short period of time, so you know what to anticipate out there. Some of the examples I have here for a design are from actually from a stream down near Platteville, Roundtree Treb. It was used for a design course down there for about 3 years. Here's the watershed delineation, topo map. You can tell, oh, pretty urbanized, which is like out of my normal realm where I work. But so you learn a lot right away looking at it. You can tell there's 2 tribs coming in right above the crossings. You learn quite a bit. So, and then also you can upfront start to identify important concerns, like for passage, road consideration, channel morphology. I won't go into a lot of detail, but the point here is if you can start to identify those upfront, when you go out to do your survey, you're more likely to collect data that will help you address those concerns. And then even early on, you can start to develop preliminary objectives for, you know, passage, road design, channel morphology considerations, that sort of thing. So, okay, so you head out in the field to do your survey. A couple of things you definitely need are a stream profile survey. And we're going to say 20 to 30 channel widths in each direction, upstream and down. You need a number of stream cross sections. I'm going to say minimum of 5 for hydraulic modeling, more is better. And then also for your reference reach, you need at least 1 and then some other just, you know, bank full width measurements there. You need obviously some survey of your road, so you can do all the engineering aspects for the road itself, culvert replacement. These days, almost everything's done with a total station, so you can get a good topographic survey around the crossing itself and then pick up all these other features. The other thing I would highly recommend, and if you're like me, I'm not an artist, so I'm always like, want to resist doing this, but do a site sketch. And there are 2 reasons for that. One, it forces you to observe more if you're trying to draw something. So here's an example just of a downstream part of a crossing, and then they had a separate sheet for the upstream. But the other benefit of it, not only from forcing you to observe, is some things are easy to survey, invert of the culvert, bing, 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 maybe obvious banks, but some are really hard, like boulder clusters and undercut banks and large wood and woody debris and that sort of thing, but yet you can sketch them in very quickly. So, and then you want to make sure that your survey includes your reference reach, or if it doesn't, you got to get back out there, and you might consider some type of you know, initial geotechnical investigation too. So a word about cross-section, cross-section location. Again, you need you know at least one good cross section in your reference reach, wherever that's located. But I've got a couple diagrams here. So this one down on the left is right from the HEC-RAS book. So if you're going to model, and they're saying minimum you need 4 cross sections. So okay, you have one downstream where the full flow has fully expanded, one immediately below the culvert where it hasn't expanded yet, you know, one above where it's contracted, and one where it hasn't started to contract yet. So a couple interesting things about this. One, you know, this is your traditional culvert design, constricts the channel, right? They're just assuming it's going to be constricted just by the way this is laid out. The second thing is that usually when you constrict a channel, like I've showed you, you end up with a plunge pool here. And so you'll have deep water right here, but then you'll have a tail crest right there. And so the way any hydraulic modeling works in HEC-RAS, it does step water calculation from here. So it goes from cross section to cross section through the structure, cross section. Well, if this is a deep hole, and this is the next one, it's going to model from there to there, and it's going to miss this high point. So I would always put a cross section through that tailwater control at a minimum. That's why I say 5, but boy, if you could get 4 and 3, all the better. So what's the diagram on the right? You know, it's actually, I got it off the web. It's a HEC-RAS blog. I've got some other examples, but the idea is that a model like HEC-RAS, it's a one-dimensional model. So it assumes the flow is like this at a right angle to your cross section. Okay, so what happens is, of course, streams, you know, meander, and so you want to cross the stream at a right angle, but you also want to cross the floodplain at a right angle. So you have to think about, for flood flows, you're going to have flow out over the floodplain. What direction is the flow going? So this one does a pretty good job of crossing floodplain and stream flow at a right angle. Well, what about here? So this flow, okay, we're coming across right angle, and now we got to turn, cross the stream at a right angle, now turn again. So this is really the appropriate way to lay out your cross section. So you want to think about that, you know, before you get out there and as you're selecting where to survey. Okay, I won't say much about geotech investigation. Sometimes you can do some initial stuff yourself, or if you know a soil scientist, some engineers, a geologist, they can help you look for, you know, some of these sorts of things can be a real problem from a structural standpoint. And the sooner you identify those things, the better. You know, and you can do that sometimes with a soil auger, hand shovel. There's even a drive probe you can use for, you know, some things. And of course, you can step up to paying someone to do soil borings and geotechnical investigation, which for bigger structures, it's probably what needs to be done. Hopefully you have a structural engineer who can take care of that for you, or you can, you know, consult with. So let's now step into some of the design aspects, but also include consideration of, you know, some of the survey details. So I mentioned you need a stream profile survey. So this is an example of how that plots out. What is it if you're not sure? Go downstream 20 to 30 channel west, bankful channel west, get in the stream, find the deepest part of the channel. So it's that way, right? So you get a reading, and I like to get water surface too. This one doesn't have it in it. And then you work your way upstream, making sure that, like any survey, that you define all the breakpoints and you can connect the lines up and represent the slope of the stream. So, and that's exactly what this does. And you can see these are pools, short riffle, pools, short riffle, and then we get into more of a straight rapids or riffle here. I mentioned the plunge pool. So here's the plunge pool, and you come up the invert of the existing culvert, the top, the road, so you can get those elevations, work upstream. So plunge pool here, this is what I talk about. If you have a cross section in here and it comes through this deep part, and then you have another one downstream, you miss this high area, which is going to control your flow. So I would always get you know, another one in this area along with the 2 right in front and behind, one upstream. So what are the red lines and the red dots? So the red dots, the other thing you do when you're doing on a moderate high gradient systems, you identify grade controls. So they're located at either the head of the riffle or a pool tail crest, whatever you want to call it, and you rate their stability. So you identify those, and then you can connect those up and get these individual slope segments. And you can also, if they're similar, then kind of start lumping them. Do that for 2 reasons. One, for the channel you're going to design through the structure, you would like to develop a design profile and connect stable grade controls if you can. So we're really lucky here. In this case, we have good stable, and this is typical at the outlet of the plunge pool. And then we have a couple grade controls up here, moderate, but we have a high, but they all line up. So, you know, it looks like a really good design profile for the thalweg of our channel going through the structure. So, and the other thing you use that for is originally we were thinking, oh, this might be a good spot for a reference reach, but as we plot things out, you know, the slope's not great. So you use this to then find, match your slope as close as possible. These match almost identical. It doesn't always happen, but as close as possible. So we actually use this for the reference reach. Okay, so we're starting to get there with our stream bed design. This is a different site, and the reason we use this site is one, you got to do your alignment with your profile because the alignment will affect the profile. The example, this previous one here down Roundtree Trib, down Platteville, alignment was pretty good at the inlet outlet, so we didn't have to mess with it. Here, we had 3 culverts set over here, clearly probably channelize the stream right here so you can put in shorter pipes. And so with the new structure, we really wanted to try to re-sort of channel. Well, this, if you're doing a stream profile survey, you're going to follow it up through here, but then you want to make sure you get enough survey data and figure out, can we actually connect up through here? And so by recognizing that up front, you can end up with, rather than this here, you can have this in here. So the idea is do those sort of concurrently. Okay, so we have a reference reach now, we got design profile. What about, and we have in our reference reach, we have some bank width measurements, typical cross section. What about our channel materials? So, well, we can go in that reference reach, identify a bunch of transects and do what's called a pebble count. A lot of you have probably done this yourself. You're gonna have, you know, gravels, cobbles, and you wanna measure at least 100 to maybe as many as 400 particles. They have 3 different axes, a short A, long C, and B, which is called the intermediate axis, and that's what you want to measure. So you want to systematically pick up 100 of these, measure this axis, and then you can plot a cumulative particle size distribution of that. Usually the measurements are made millimeters, but you can convert those to inches. And then you can start to break this up into sort of logical groupings and size classes. So like this first line is like 3/4 inch minus. So you could bring this across, say, oh, for our bed, we want 28% of our bed material mix, whatever volume we need, to be 3/4 inch minus. You always want at least 5% sand or finer so that you can fill in some of the voids in the sub bed and that the base flows won't go subterranean, become a fish barrier. So, and then you can say, oh, we want 22% from 3/4 inch to 2 inches in size, 20 and 2 to 4, you get the idea. And then you can go to a quarry or gravel pit and specify the volume you need in all these different size classes for your bed mix. The other thing you need to do though is you need to build banks, and we won't get into like, you know, specific bed features and all that, but you might need some larger stable material for the banks and some of the bed features that stay stable throughout the life of the structure. So your first estimate of that is finding what are called key pieces, and you want at least 10 of those, maybe as many as 25, measure those, and it really pays to measure the A, B, C, and C dimensions of those, and they'll serve as your basis for your stable rocks in the structure. So, okay, so we're getting there now where we have the basics of the design bed going through the structure. Well, what about the structure itself? How do we wrap a structure around it? Well, you got to think about width. Got to be bankful width and room for your banks. Any other, you know, considerations that might expand that out. We're going to look at something called an LVAP, lower vertical adjustment potential, in a few seconds. Select an initial structure, ID or min-max cover requirements, you know, where you can put your footer invert, again, verify cover, think about your end treatments and the length of your structure. What kind of side slopes you're going to have? Are you going to have head walls or anything to get your structure length? And it's sort of an iterative process, and then eventually do your hydraulic capacity check and your sediment mobility stability check. And, you know, you refine things as you have to. So here's the example. what's that LVAP, lower vertical adjustment potential? It's really a scour analysis. That structure is going to be out there 75 to 100 years. What kind of scour might it exceed or experience? And so the idea is to use the channel geomorphology to give you, to allow you to predict that. So you find the deepest pool outside of the plunge pool in your whole survey area, not just in reference reach. So here it is. Here you figure out the residual pool depth, and then you apply a little bit of safety factor for that. And then at every single pool, you can come down that same depth. So this is your prediction of over that long period of time, with a variety of floods occurring, that sort of thing. You might have some scour occurring in your structure that could possibly get that deep. So you want your footer or invert to be below that level. So now, so we have a depth for our structure. We have a design profile for our thalweg. From the cross section with the banks are. We also have banks above and below. So all that kind of connects through pretty nicely. So we're ready to start thinking about structure and wrapping the structure through. Here's a typical profile from the reference reach, 15 feet wide. Want good stable banks, so maybe rocks up to 2.5 feet, 2.5 feet. So you add 2.5 feet on each side, gets us up to 20-foot width there. So you can put the LVAP on here. So in this case, with this size structure, it seemed to make sense to think about some kind of a con span as one option. So here's a 20 by 8 foot con span, could be set on footers. So here in case you want the footer to extend below that lower vertical adjustment potential, come up to bank full. So why bank full? Well, that way you can put in your footers, build this entire bed where it's open. You can get at it with an excavator, heavy equipment, much easier to build. You can build inside structure, but it's easier. And then put the lid on, backfill and that sort of thing. So it's a nice way to go. Here's an example of that whole concept again of, a lot of structures can work. Here's this channel is identical in all these structures. Differs is maybe the amount of floodplain. And as long as you meet your LVAP cover requirements, theoretically, any of these structures could work. 2 are bottomless, 3 have bottoms in there. So it's that idea of, design your bed and meeting your engineering constraints and selecting a structure that works best and maybe at least cost. Some real life examples, Northern Wisconsin, these 3 have inverts, bottoms, these 3 do not. So, and then last slide here for, the high gradient stuff. You do your hydraulic modeling here, 100-year flood estimate, 390 CFS, small watershed, so 609 CFS, really, really response flash sheet of runoff. Good headwater to depth clearance here, so no problem there. And then you can use the hydraulics to do that sediment mobility, stability analysis I talked about. The idea there is you want your particles to be stable. The big ones got to be stable across the whole range of flows. You want the bed, the basic bed, like when it starts to mobilize at whatever flow in the reference reach, you want it to mobilize in the structure too, so that it maintains that continuity of sediment transport. So I have a summary here, but I'll leave that for your reference, on kind of the design steps, and then I'm going to move on to what I'm calling the very low gradient considerations and design. So again, you might only want to do this where the stream is transporting sand and organics, not a mobile gravel bed. You don't want a culvert that's greater than or equal to bank full width. And if you're not going to build bed and banks through there, the idea is that the size of the culvert sort of act as the bank, so to speak. Got to get set at the proper elevation, analyzing stream profile. Part of that is determining that you have natural backwater that provides good depth and low velocity for AOP. I call that good D, low V for AOP. And then still verify hydrology and hydraulics at headwater depth ratio 0.8. You want to pass at least 100-year flood. And then while in some cases you may not need banks, there are times when you may need them or you may wish to add them, or you may need to do some stream restoration also. So from a site assessment standpoint, not a lot to say other than you don't have to worry as much about the bed materials if it's sand, but man, the profile. find a good reference reach for your bankful lifts, and you really got to analyze that profile, especially for prior impacts. A lot of these existing structures have impacted the channel morphology upstream and down, so you got to kind of consider that with your replacement. So a note about survey, I think all the other things apply, but in these very low gradient streams, you may not necessarily have pools and riffles. So there, though, a lot of times the deep spots in the bend. So I would try to get, bend straight, occasional bankful if you got a good bankful somewhere. If you have a much longer, straighter stretch, then I would try to get a point every half-foot channel width maybe. And I would also always get the water surface. I think it's really helpful. I have a few examples of that, I think. And then if you do have a culvert that's constricted, set too high, and you have some aggradation occurring upstream, you can try to get the surface of, if it's muck, surface of muck, and then probe down through to see either where the sand is or the gravel, or if it's sand over, is there gravel underneath it? Do we think some of that's going to move with our new structure? So that can help you determine like how the channel might adjust and restore itself with a bigger culvert set lower. So example, bankful width is Riley Creek on the Nicolay part of the forest. Stream is flowing down this way. So crossing there, here's a good kind of straight stretch where you could do some good bankful width measurements. Is unimpacted by the crossing. You got to be careful going upstream if there's ponding. You got to find kind of an unimpacted reach. Bankful width varied from 7 to 11.5. Mean of 9, this was a 2.25 square mile watershed. So again, you could do some representative measurements here for bankful width. I've got a bunch of details here on culvert elevation. I think you read them, but there's a number of things I think to consider as you look at the profile. So let's just jump to the example. Here's Riley Creek, and you can see the low gradient. Here's our stream profile survey, the Talladega stream coming upstream. You don't see pools and riffles. You do see some deep spots. A lot of times they're in the bends, and then you see a relatively flat water surface. I stress try to survey the nearest 100th of a foot, but you see bounces around a little bit. So, but we got close to that anyway. And as you move your way upstream, you come to the culvert, you do see somewhat of a plunge pool, but you see these high points here. Well, that's over a 5-foot distance. There are a number of rocks placed there to try to facilitate fish passage there. But you can see how high the culvert is set here. Here's the invert. It's over a foot above, the stream bottom here. And that's raising the upstream water level 1.1 feet and ponding back. It's just starting to climb a little bit, but it's ponding back 300 feet. We probably should have surveyed further upstream. Just kind of eyeballing it, even though you have these ups and downs, these deeper spots and bends, clearly this channel is graded. And if you walk out there, there was organics on the side, sand in the middle, but at a graded, almost a foot. So the idea is to put in a bankful width culvert set much lower, kind of project how the stream might restore itself. So here's kind of a design profile. So if you set the culvert down here, we anticipate at least a 1/2 foot to maybe as much as a foot of some of the sand would move through there and fill in the culvert. Even at a lower flow, we still should have good depth and low velocity, and this will all adjust over time. So what does that look like? So the culvert was both a constriction, I don't know if I pointed it out here, it was 68% of bankful, so that's constriction ratio. But it was also set high. So what would happen if we took that same culvert set lower? Well, you still see what the constriction does, and this is better. And this is better than some crossing I've seen, but still doesn't meet the criteria. So even at a 2-year flood, the culvert is almost full, and as soon as you get above that, it starts to pond water back, and it had water depth ratio of 1.5. So if we go to bankful width culvert, just barely to the minimum bankful width, a little over 7 feet, all of a sudden we're passing that 100-year flood with a headwater depth ratio of 0.65. If you want to think in terms of flood flows, so pretty moderate flood flows, only about 25 CFS per square mile. And this is very typical in northern Wisconsin, where we have these sort of moderate, 100-year floods or flood flows, and we get a bankful width structure. Usually we will pass these flows with some freeboard here in less than headwater depth ratio 1. Talk about skew again. Here's kind of a borderline situation, and the problem in the sort of connection between profile an alignment. So we have a stream coming down here, follows the stream, probably was channelized, put in a shorter culvert, turns, does a 90, comes through here, heads downstream. So, the ideal thing would be, gosh, we could, reconnect that. That would be a nice way to go. You have better alignment at the inlet. The problem is you're going from, these were 2 4-foot, 45 feet long concrete pipes with a rock head wall that was failing. They were starting to separate. So, the problem is all of a sudden we have to go to almost 100-foot culvert. And then, do you need to build a stream bed through it? And the conclusion was, yes, we would have had to. If we tried to put in a flat culvert, it would have been buried too much here, caused a head cut upstream. We were at that kind of break line on a slope of 0.6% using the water surface. If you set the culvert at a slope, would have been too shallow here if you're thinking this is a stable grade control. So you either do this, build a full bed through it, long culvert, more of the stream in the culvert. This channelized section looked like that was pretty stable. So the other option was the gradient's pretty low through here, 0.17%. So that's actually because we weren't aware of any kind of a woody debris problem. We went with a 30, I think it was a 31-foot box culvert right here, 16-foot versus the 2 8-footers. So, but those are the kind of trade-offs you have to think about and you have to make, and you got to tie in the alignment with the profile. So another example of like bends, just a word about this. This really is a no-no from my perspective. Couple reasons. One, it shortens the stream, so you permanently lose aquatic habitat, or at least for those 50, 70, 100 years of structures out there. For that reason alone, you probably wouldn't get a permit for this. But the other thing is it shortens the stream. You shorten the stream, you increase the slope. You think back to that lane diagram. If you increase the slope, what can happen? You can cause degradation or a head cut moving upstream. That's what I talked about in the last example. This is pretty good if you can't relocate the road. Ideally, you like to cross at a straight stretch. Sometimes you can't do that. This is a nice option, if relocating it isn't feasible. Here's an example of that. Here's right on a very sinuous, larger, low gradient sand bed load stream, right on an outside bend. Culverts are failing. There were 3 culverts and a head wall. And so no opportunity to relocate the road because of some private cabins nearby. So this box culvert was put in. It's very short. It's only about 1 bank full width long. And so it doesn't really, constrict the sinuosity of the channel that much. And what happened was the stream actually builds a point bar on the inside bend, scours more on the outside, can move that sediment through. So it really maintained the continuity. And I think the fact that it's so short really makes a big difference in that it spans bank full width. So I mentioned, in a lot of cases on these very low gradient streams, you can get by with the sides of the culvert as sort of the bank. So here's some examples of that, no structure inside it. As an aside, talk about stream restoration. This old crossing, not only was fish passage barrier, but was ponding water upstream, was class 2 trout stream. You can imagine the water temperatures up here by putting in, larger culverts at lower, restored almost a half-mile stream, reduced water temperatures, all for the cost of a road stream crossing replacement. Here's this idea, low D, good, or good D, low V for fish passage. So keep moving here. So if bank full width is good, is wider, better? Well, not. Maybe if you're not going to build banks through the structure. So where you have a mobile sand bed, when it moves into a structure, if you don't have banks here, it spreads out uniformly. Spread out uniformly. Here's a good example of that, straight, uniform. And if you have low flows, a real wide structure, that shallow water can impede fish passage. So we certainly don't want that to happen. Another example in southern Wisconsin, got a just under a 12-foot bank full width stream, moving sand, moves a lot of sand. You come into this bridge, 16-foot wide bridge, so it's quite a bit wider and bankful. That's good from flood capacity standpoint, but you can see what happens because of the shade. You don't have any vegetation growing. That's what provides the stability for the banks. So then the sand spreads out uniformly. It's kind of hard to see here, but if you can see my mouse pointer, that's all exposed sand. There's some exposed sand over here, extremely shallow. So nothing wrong with the span. I like the span. I just think building some rock banks through or some other rock structures to form a low flow thalweg would be the solution to that. So, and here's an example of that. We've got a few cases where we had a co-op project, highway culverts, 100, 130 feet long, 7, 8 foot, with small groundwater fit streams connect up to North Branch of the O'Connell River. So we were concerned about that happening. So what we did is went and built rock structures and tried to place them to think about that scour and deposition. So to create some differential scour here and then deposition around these structures. And they were kind of theoretically laid out to match, a standard sort of stream geomorphology concept is 1 meander wavelength is about 10 to 14 channel width. So in this case, we said, well, we'll use 10, 8 foot wide, so 80 foot, and we wanted to build like 5 structures in that 80 feet. So that's how we kind of laid this out, tried to figure out how to structure these so that we can force the low flow thalweg back and forth and topped them out at about the bank full elevation. So probably not perfect, don't look exactly like a stream, but certainly much better than that wide shallow situation. And then here's just an example of one of those sites, and they culvert before and culvert after with the sand bed. And in this case, we set some of the culverts on these very low gradient streams. You have a 10 to 10s, 50 foot culvert. It's not worth setting at a slope, I don't think, because you're only talking about 500s or 10, 1500s foot. But as culverts get longer and the slope increases a little bit, we were kind of right at that break point again. We did set this one, those at a slope. Last topic here is, on that identifying issues up front. This is a cooperative project with 2 different agencies. Highway culvert, Turby Creek, not only fish passage, but animal passage was an issue identified in Forest County, Potawatomi. They wanted mammals to move through here, even possibly deer and bear. So 4-foot banks were designed into the structure to provide that opportunity. So the earlier identify those things up front, the better. But those are the sorts of things you can do if you see the need. And one last example of stream restoration is a small stream. Look at the stream profile coming up here. Here's the stream, flat water surface. Then all of a sudden, over about 100-foot stretch, the stream bed climbs 1.5 feet or 2 feet. Water surface climbs, goes up through the culvert, and is ponded upstream. So what's happened here is this repeatedly failed sediment downstream. The fines may have washed away, but then this deposit for about 100 feet of road gravel that the stream couldn't move set there. So, and then upstream, of course, you had organics filling out. So the idea is try to restore the stream profile, put in a bank full width culvert set 3 feet lower, and then remove some of this material. So these are cross-section locations. This was our design profile. Go from these cross sections down to, so excavate about 1.5 feet of material and try to restore the profile of the stream. And so sometimes you'll run into these things and you have to make that decision. Would we like to restore that stream profile, the continuity of the stream, and that sort of thing. So that about does it. Same thing. I've got a little summary here, but I'm not going to spend any time on that. I'm going to move on, keep moving, talk about flood resilience and ecological culvert design. I think it's pretty obvious why they tend to be much more flood resilient, and that's because of the greater flood capacity and freeboard. So again, here's another example, Q100 headwater depth ratio of 0.53. Okay, and lots of freeboard capacity here. Again, flood flows almost a 5 square mile watershed. This was 11-foot wide culvert. Flood flows pretty moderate, down around 25 CFS per square mile. So, but the other thing stream simulation and ecological culvert design does is it helps with woody debris passage. And I'm going to reference a study here from California. I'm not aware of that many studies on wood passage, but here's one from the early 90s, Northwestern California. But the thing I want to call your attention to is this box culvert here, and look at the debris piled up. 2 cells, and you see so many times where you have multiple culverts or multiple cells. I haven't really talked about that, but one opening that's 2 or at least beyond bank full width, and that'll help tremendously. If you go multiple openings, you're just creating a failure problem and a maintenance problem. So they did a number of things in that study, and they looked at culvert plugging map, but they identified over 3,000 pieces of wood that moved. 99% were shorter than the channel length. So, which kind of makes sense that most pieces moving, if they're longer than bankful width, you'll start to get hung up. And so that's a good thing, but there are some that move that are longer than bankful width. So I'm going to pop on to their kind of major conclusions of what will promote wood passage, and stream simulation or ecological culvert design pretty much ticks all these off. No headwater ponding, so you avoid this situation here. No constriction. So the vast majority of that wood that's moving can move on through the culvert if it's less than bankful width. They want freeboard on concave slopes. Well, we have it pretty much everywhere. And then the other thing is good alignment at the inlet. And so the idea here is that there are some pieces that may move that are longer than bankful width. And if they are going to move, they're probably moving parallel to flow. So if you have good alignment at the inlet, then the odds of them moving through are much higher, as opposed to a situation where you have that poor alignment at the inlet. So those all help to minimize both failure and maintenance problems related to woody material or woody debris. And then the last thing is abrasion, So we've probably all seen this where, this part of the culvert sound looks good, but the bottom's almost shot from sand, gravel, constant abrasion. Here's a structure and it had, I think, failed or was removed. And so all these, and it had only been in around a little less than 20 years, all these light spots are sunlight shining through. There are holes in the culvert. So you really need abrasion protection if you want a flood resistant culvert that's going to last, 75 years or more. So, and ecological culvert design will give you that, especially you build a bed and banks through here. But even if you have a natural sand bed, develops can provide much more abrasion resistance, will really extend the lifespan of the culvert. So, what I want to say then, and sort of in conclusion, is that using ecological culvert design stream simulation will get you a long, long way towards flood resilient culvert. But if you think about those range of kind of flood flows I showed you for 100-year flood, you can think about watershed characteristics. And some watersheds are going to be more vulnerable to flood flow increases in the future if you're thinking about climate change. And hey, we're putting a structure in today, and I want it to be out there in the year 2100 or 2110. And so what watersheds are going to be more vulnerable? Well, heavy, shallow soils, bedrock, minimal storage, steeper slopes, and then the opposite end of the spectrum are going to be these real heavily groundwater fed, systems with high infiltration rates. They're going to be more resilient. So you can think about that. You can even think about site characteristics. Certainly narrow floodplains, steeper channels can move more debris, higher velocities, higher fills, more catastrophic failures, that sort of thing. So if you have certainly the watershed, maybe the site characteristics, you could consider some additional design elements to reduce vulnerability, increasing structure size, providing overflow areas if possible, although in entrenched systems that becomes more difficult. Larger riprap, higher up or at overflow areas, and then concrete structures certainly are more durable. So next thing I want to do with regard to flood resilience, I just want to show you some examples. In July of 2016, Ashland, Bayfield County, northwestern part of the state got hit with an extreme flood. Up to 9 inches, some cases maybe more, fell over a pretty broad area in a 6-hour period. Catastrophic flooding. I know the Great Divide Ranger District, northern half of that, and Chequamegon, Nicolet National Forest, I think they had like 400 miles of roads closed because of all these washouts. But in the 15 years preceding the flood, Forest had installed a number of these bankful width ecological design culverts. So I want to show you some of those because, well, a few failed and a large number survived. So here are 4 of those bankful width culverts, or slightly greater than bankful width. And all of these overtop just slightly, right here, over here, here, but not enough to even require any kind of road maintenance or loss of gravel. Now, one of the things we were able to do during the flood response is at these sites get a high water mark. And because it had been replaced in the last 10 to 15 years, we already had an existing grass model all set up for the design culvert. So we could run that model and match a high water and get a flood flow estimate. And then we just compared that to the 500-year flood for the regression equation. So you see these numbers here, our estimate was anywhere from 1 to 2.7 to 3.6 times the 500-year flood. That's the flood, it's an estimate again, and there's some noise in there, but what these experienced and survived. And so then also where you have slight entrenchment and overflow areas, that helped a lot too. So you have bank full width culverts. These are two examples. This is same site, road over top. This one with the box culvert from here to there, just a minimum on sediment, a gravel loss off the road, very minor maintenance. This one, much more substantial loss of gravel, but the road with a little bit of maintenance opened up. Most of the gravel was, in the ditch here. And this one, 2 to 3 times our estimates of the 500-year flood. So certainly not designed to handle that, but they survived it in pretty good condition. Another thing I'll mention, a lot of the smaller streams, we used pipe arches, and we always use a step bevel with the idea that if you do have any debris moving and it starts to plug, or beaver, especially beaver, as much for beaver, there's room for water to get over the top and still get into the pipe, and gives maintenance crews time to get there and clear it out. Where if it's flush cut, when it plugs up much faster, and it's hard to clean out without damaging the pipe. So just a little bit of an aside. Another example here of that slight entrenchment with overflow is a crossing. It failed in 2013 at not very high flood flows. It's probably like a 5-year flood or 10-year flood. And it had failed a few years before that. So we know it failed at least twice in the preceding 10 years or so. Constriction ratio 0.8. New culvert installed bank full width in 2014, was in the flood area. Here's the modeling for the new culvert, and headwater depth ratio 0.8 at the 100-year flood estimate of 69 CFS. So it was 0.6 square mile watershed, so around 110 CFS per square mile. A little more flashier in some of the ones I showed you, this getting up in, wouldn't you know, where the flood hit is one of the area that's most responsive to runoff. It's the old Pinocchio-Gibbik range, but the estimated flood flow from the flood was 450 CFS, overtopped the road, but not at the culvert. It was off to one side. Did wash some of the road surface off, but the whole crossing survived, need a little bit of maintenance. So having that overflow area off to one side certainly helps some of these structures survive. This is another example of what that looks like on design drawings, and I think I'm going to try to zoom in here if I can. So here is the plan view, existing crossings, 3 pipes, 24, 18, 12, washing out all the time. You can see a braided channel from all the sediment downstream. Put in a bank full with culvert, set at a much lower elevation. So if we move down here, here's the bank full with culvert. Here are the 3 culverts that inverts at 2 feet lower. And the thing is, it would have stuck out. Here's the road profile for the, the existing road. So had to ramp up and over, add fill to the road, try to minimize that as much as possible to get a sufficient cover over the pipe. But we've always said what that does is it provides an overflow area on either side of the pipe. And that's exactly what happened. 2016 flood did overtop on this side. A little bit of gravel was lost off the road, but the structure survived. So having those slight entrenchment overflow areas, I think really helps. But I think it also helps that, I'm going to go back to here. Part of what happens with the bank full width culverts is the tailwater and headwater come up together, and they don't start to separate till you get to a really extreme flood. And even then, the difference is not as great as if you have a much smaller culvert that's constricting at much lower flood flows. So that's the point there. Comment here, just concrete structures are pretty durable. So these are structures that survive the flood. Here's one with the stream bed constructed through it, Preemption Creek. It's built in 2007. we estimated 1.6 times 500-year flood. The road actually overtopped a little bit. So we got pressurized flow, which is what we don't want to see that. The culvert, sure enough, we lost some of the bed, some of the banks, but the point is these large key pieces, and in particular, this is after the flood, you see these, you don't even see them in this diagram, they're buried in the bed. And they no doubt helped hold things together in some of the larger pieces. There was one of those structures up here. So, but again, to be more flood resilient, a little bigger pieces might have survived even though the full structure overtopped. So with that, I'm almost done. I just have one or two slides to talk about costs very briefly. I am not an economist, but I know for sure you start talking about putting in bigger structures and it's going to cost more and people get very concerned about costs. So I just want to touch on that briefly. So here, Bob Gubernick looked at a number of structures, stream simulation structures put in the Pacific Northwest area. And he found for a 50% increase in structure width. So he was looking at like going from 8 to 12 or 10 to 15. The cost of the project went up 20 to 33%. So to me, it's a pretty good deal when you start thinking about the increased lifespan, the ecological benefits, the reduced maintenance. So, you know, I think that's, to me, a pretty easy sell. Another example here, Gillespie et al. This publication I've referenced for that. Hurricane Irene hit the Northeast back, I think, around 2011, but devastated, you know, areas in the Northeast. This in Vermont, Green Mountain National Forest. They had installed 3 stream simulation crossings. Most of the area looked like this, but their 3 crossings, you know, look like that. And looking at what it cost them over, I think it was a pretty substantial quote H&H design, but we're only ended up being 9 to 22% greater. So to me, pretty good deal. And you got to think about the value of these crossings if they survive a flood in terms of the emergency response and the safety aspects. Is pretty tremendous. So a little closer to home, publication from 2016, John Simonson helped facilitate this actually. And this was like a modeling study done, I would say, for the northeastern part of the state. And they used a road stream crossing inventory. And from that inventory, there were 460 culverts that had sufficient data where they felt they could do a lifetime cost benefit analysis. So this is, they were able to estimate costs for culvert replacement for ecological design culverts versus, you know, in kind, estimate their lifespan, what kind of failures they might experience, kind of a modeling exercise, what the maintenance costs would be over the life of the structure, kind of discount, you know, the prices. And what they concluded was the ecologically designed culverts, in spite of costing more to install, had a net fiscal benefit like 50% of the time. That was more cost effective. And they also concluded that that was especially more common with small culverts, less than 5 feet wide, were the most cost effective. And not surprisingly, those benefits accrue from a longer lifespan, reduced maintenance, greater flood resiliency. And they don't really include, it's hard to put numbers or cost value on the ecological benefits. So you think about those structures lasting, say, 75 years, you throw the ecological benefits on top of it. We're trying to do something similar in the flood area with 16 survivors out, I think 17. We've got the construction cost estimate to cover a number of years. So anyway, this still needs work. It's work in progress, but I would say it's starting to look like it'll mirror these results to some extent. So I'll leave it at that. Just 1 or 2 little items. I've got a few references here for stream simulation, ecological culvert design. These are publications you can get. They also have a big, thick user manual, but you can download it as a PDF from this site. And then a couple of those cost publications I just showed you, you can download from here. One last little item I'll point out that Dan Cinderelli here, Bob Gubernick, Mark Weinhold, they teach for the Forest Service a stream simulation course. It's a 1 week, 4.5-day course. Usually they try to do 3 per year. There's no tuition. They move around the country. Usually region has to sponsor them. So if anyone's interested in taking that course, you got to get to wherever the course is. Let me know and I can try to find out what their plans are for this year and if they have any openings or not. And with that, I am done, so I will stop sharing and mute my screen. I want to just thank everyone very much for their interest.
Thank you, Dale. That was great. And thanks for sharing all that information. There's been a few questions put through on the chat box, but in order to keep things moving along and make sure we have kind of time set aside for a more in-depth discussion with you, the attendees at the end, I'm going to keep things moving to the next section, and know that if you asked a question and haven't received an answer yet, we have that pulled onto a separate document so we can talk about it at the end. So stay tuned for answers to that. We're going to jump right into our next session. This is looking at construction and permitting tips and best practices with Maureen Millman and Bobby Joe Fisher from Wisconsin DNR. So Maureen and Bobby, I'll let you to take control and get started with whoever's going first in that.
Thanks, Chris. Can you let me know when you can see my presentation? Can anyone see my presentation?
Not yet. It's loading right now. And there it is.
Okay, great. Just to introduce myself, my name is Maureen Millman. I'm with the Department of Natural Resources, and I am the Municipal Transportation Policy Coordinator. And that means that I work with transportation liaisons throughout the state on policy and procedures that are related to transportation projects, municipal transportation projects. So I'm here to talk to you today about permitting. What do we do for permitting? We're here to talk about road stream crossing projects, and where do we start? The first place you want to start is to think about what kind of project you have. If you have a public road project that's open to the public for transportation, you want to talk to the DNR transportation liaison in your area first. If you have a private road, driveway, trails, at that point, you'd be talking to the DNR water management specialist and applying through our e-permitting process through DNR. But we're here today to talk mostly about public roads and can answer questions about any kind. But today we're going to talk about road stream crossing projects and focusing on transportation. So get to know your project area. The first thing you can do is look at some maps. Will your project be impacting a waterway or a wetland? DNR has a number of maps. On the left, you can see one that shows our waterways. On the right, you see one that shows hydric soils, which may be an indicator that you have wetlands in your project area if you see that. And that's, those maps are sort of a guide to start you in the right direction and to start you to help you to determine if you need a permit and who you might need to talk to at the DNR and at other agencies. So you're also going to go out in the field. You're going to look for wetlands next to the road. Permitting through the DNR is going to be if you are potentially impacting those wetlands or waterway. Here we're going to be focusing on waterway, but along with waterways, of course, we often find wetlands. So going to the DNR website, when you have a public transportation project, you can just type in keyword transportation. That'll take you to our web page. And right on that first page, you can click here, and that'll take you to the list of liaisons showing what counties they cover on the map. This is actually a document that's a couple pages long, so you can also get to phone numbers and supervisors and see who's in what county that way as well. Like many of you, we are still working at home, and so email might be best for contacting your liaison right now. Other people you may need to contact before you begin your project: local county shoreline zoning folks, U.S. Army Corps of Engineers, and the liaison can help you to determine if you need a stormwater permit as well. If you are working on a project that has state or federal funding, then your project may fit under the DOT DNR cooperative agreement. So in those projects, they are not permitted the way that other projects are. Rather, DOT contacts DNR very early in the scoping of a transportation project. DNR reviews the projects for impacts to wetlands, waterways, wildlife, threatened endangered species, and protected lands. And then DNR continues to work with DOT throughout the planning and construction of a DOT project. Back to our website, the place you want to go is where it says highways, and that'll take you to our page, which has everything you need to know about general permits and individual permits. On that page, you'll find the general permit that has all the information of what's included, what kind of projects are covered under the general permit. We also have a checklist. You can fill out a RAP form. Some of you may have done that in the past. We also have an information worksheet for the municipal transportation projects that I'm going to talk about. You can also contact your transportation liaison. Again, that we ask that you start there just when you're starting to scope your project. And then we also have information on individual permits, should your project need that. So when does a municipality need a permit on a road project? So the general permit is called, we call it GP2, a general permit 2. It's for the construction, reconstruction, and maintenance of a highway, bridge, arch, or culvert on a municipal transportation project. So the applicant has to be a municipality. If the impacts are less than 10,000 square feet to the wetland, and you may be eligible for the general permit. And there are 24 eligibility standards that need to be met in order to be eligible for that general permit. Otherwise, it may fall into an individual permit. So I mentioned the information worksheet. This is something that our program created that's unique to municipal transportation projects. We were really trying to hone in on just kind of the basic facts so that we could use this to determine if a general permit was needed, if the culvert may qualify for an exemption. It's also, and it can be used in place of the RAP for general permits. And it's also great for record keeping. As I talk about the culvert exemption, there's a lot of misinformation about there. But another aspect of that is that as the public entity that's in charge of a road, you have a responsibility to keep information on culverts that you replace and any structures within your county or your township or whatever it is you're in charge of. And this can help to keep some of those records. If you have situations, Dale mentioned the flooding of 2016, a lot of culverts were washed out, a lot of structures were impacted. And if the people who were in charge of those structures didn't have good records, they may not have been eligible for FEMA funding or any other kind of emergency funding that may have come up. So it's important to keep that information and have that on file. If the project impacts an acre or more, you may need a stormwater permit. And then there's also the possibility of Army Corps permit as well. So we have links to those on our webpage as well. I mentioned the culvert exemption that came about in 2015, and we continue to kind of show what the exemption language actually is because there's a lot of misinformation regarding what fits into that exemption. So again, that's another reason to talk to your transportation liaison about what that really means. And a key aspect of that exemption language is best management practices. So those are the practices that are really simple and effective methods that use before, during, and after construction to make sure the project's going to be a clean project and using best practices to build that structure. So early coordination with the DNR is key. We may have an on-site meeting. We're not doing that right now. Hopefully, maybe towards summer and fall, we'll be able to do that again. And you want to be looking at if the culvert or the road is taking a beating, and the transportation liaison can have that conversation with you when they are able to come out. And then the transportation liaison would also talk to our regional experts regarding navigation to determine if navigation is an issue at the crossing and how a structure would accommodate that. We're also going to look at threatened and endangered species and talk about habitat connectivity. Dale showed some structures that included not only aquatic organism passage, but also passage for terrestrial as well. And in some parts of the state, we have some really great species of plants that are right next to the road. And we can talk about how to avoid those or how to best manage that within your right of way. And as Dale mentioned too, sometimes a ditch isn't a ditch. It may be a stream, or it may be really important ditches, as he mentioned, the ditches that Northern Pike use in the Green Bay area. So again, another reason to talk to the liaison and have a conversation about what you're looking at. And when it comes to ditches and ditch maintenance, sometimes you need a permit and sometimes you don't. And we have lots and lots of experience working with water and roads and water next to roads. So coordinating with DNR and Army Corps on a solution that is good for your road and also impacts the wetlands and waterways less is another reason to have that conversation with us. And also to determine if you do need a permit or not. So again, we're here talking about properly sized and placed culverts. Structure is going to be more resilient to floods, which means reduced closures and safer roads, less debris getting stuck. Dale talked about that quite a bit, less maintenance cost. Improved stream connectivity brings healthier fish and wildlife populations, improved water quality, increased recreation and tourism benefits. And what it all comes down to is a longer structure like life is money saved. So on our DNR tab, another thing you can check out is the Learning tab. And on that, we have tools to assess road crossing structures, contacting our experts, some of who are on our call today that you're going to be hearing from next. Tools for culvert inventories and tips for using structure, using to assess the structure and using LiDAR. And then also presentations from our previous road stream crossing workshops. So I just wanted to thank you for having us on today. And if you have any questions, feel free to contact me. And as Chris said, I think we're going to take some questions at the end. So I'll hand it over now. Thank you.
Thanks, Maureen. And now we'll have Bobby Joe jump on and give us her session.
Thank you, Chris. Please let me know when you're seeing the slideshow.
Got it up and see it in presentation view right now.
Fantastic. Well, thank you so much for having this workshop today, Chris, and thanks to you for helping make that happen. And thanks to all the folks who are presenting today, as well as all who could join on the call. I'm going to talk today about construction and aquatic connectivity. I have been doing this work for 20 plus years, first as a specialist, a transportation liaison, and now in the capacity as a supervisor. So I am been working with the aquatic connectivity team for quite a few of those years, and I'm thankful for the patience and the knowledge transfer, hopefully, that has occurred from the experts like Dale Higgins. So thank you very much for this opportunity to talk. Also, I'm going to thank the central team. That's the staff that I supervise from Green Bay to La Crosse. Thank them so much too, because some of these slides are from their projects. Wanted to brush up what I had with some more recent photos. So I thank them as well. So there are many structures that can accommodate aquatic connectivity. It doesn't necessarily have to be a structure that is bottomless. The two structures on the left and center are structures without bottoms, but the one on the right is also a structure that has a bottom, and it's meeting bank full width. So like was mentioned earlier by Dale, as long as it's meeting that bank full width criteria or approximately bank full width, and it's set accordingly according to that lateral adjustment potential, that scour line that he had talked about. Structures with bottoms can and do have a place in this aquatic connectivity discussion. So I just want to make sure that we're not telling you you have to use bottomless structures for all these. In some cases, it makes more sense. In some cases, it doesn't. So each site is unique and the resources are unique. So I'm going to show some before and after photos of projects. Some of these projects are simple projects and some are very complex. The pictures you'll see range from, $25,000 culvert replacement up to a $1 million buried slab span bridge with lots of intricacies. So you don't have to spend a lot again, or you don't have to have a certain type of structure to accommodate aquatic connectivity. There's a wide range of options that can apply. I'm not going to go through all the details of these. I just kind of want you to see existing versus what we're talking about in this workshop. So here's a local road stream crossing replacement. Here's one on a DOT right away. This one had a stream simulation. It was a steeper slope channel. They did a little more channel armor than what we normally do in this workshop, but you can see obviously quite the improvement from the before. Here's another structure. Again, this is a small installation, but you can see that pipe on the right is set deep, natural bed material starting to mobilize into it. And it doesn't have the plunge pool anymore that the before picture has. And here's another one on a local road. This one is a bottomless pipe arch that was replaced with a round pipe. I mean, the round pipe was replaced with the bottomless pipe arch. And here's a little more advanced one. This is that buried slab span, quite a bit larger, had accommodations for wildlife passage under this one as well as human passage. It connected two state lands underneath the state trunk highway, so folks weren't going up and over the road. Same thing for the critters. The reason, I'm going to go back 1 second. The reason why I show these again, I'm not going to have time in my very brief presentation to go over how to construct, nor am I an expert in that field, but I just kind of wanted to give you a flavor for what a structure with aquatic connectivity looks like. Very often in construction, if the design folks are not talking with the construction folks, things can happen in construction that you worked so hard to address in design. And oftentimes with these aquatic connectivity structures, you're going to be setting the structure, if it has a bottom, very, very deep compared to a conventional design. Again, trying to get underneath that scour line, that lateral adjustment potential, trying to get deep into the bed so that it lasts that life of that structure and doesn't have to be replaced sooner. So oftentimes you'll see in construction a structure like this where you can see the stream bed in the background. It seems pretty high compared to where this structure is going. Again, we're trying to get underneath that scour line. This one also will have material put in, so there had to be accommodations for that. And if your design staff haven't made it clear in the plans what your function is or what you're trying to do here, things can happen in construction where that gets changed. And then all that work to have a longer living structure set deep enough, that all kind of goes out the window. So having good conversations between the designers and the folks doing the construction is very important. I'm going to address in-stream erosion control and construction because with aquatic connectivity projects, it can be a little bit different. There's different things to consider. You're digging a deeper hole, you're going to have more water to dewater out of your work area. You're potentially, if you've got groundwater, that is, you're going to maybe be putting material in the structure. That's different. You may be washing fines into the bottom. the bed that you're making through the structure, that's going to require more water and more treatment. So I'm just going to step through the erosion control procedures when you're actually in line with the stream doing the construction of the new structure. This is taken from Indiana DOT's best management practices for stormwater. It's their field guide. And so this is not something from the state of Wisconsin, but I feel like it depicts pretty well the situations we deal with here in the area. So that's where this drawing comes from, and I'll step you through it. The first thing, the first in-stream type of erosion control to protect water quality that we're going to address are the impermeable barriers. So some kind of impermeable barrier upstream and downstream. The flow comes from the left, goes to the right on this photo, and the blue C lines here and the reverse C are the impermeable barriers. So that could be sheeting, that could be sandbags wrapped in plastic, depending on, you know, what kind of stream you're dealing with. So this is just a photo, an example of an in-stream barrier. Impermeable barrier, the water is coming from the top right to left. This is a trench box wall. So you can be creative with this stuff, and an I-beam that's used to give support to that. That is, the water then unfortunately makes a 90-degree, which isn't optimal, but you know, if you're putting the culvert right back in where it is, sometimes you have to deal with a little bit of not having it just right to make your structure sit well in the crossing. So it takes a 90-degree here, it goes into what's called a bypass culvert, and then it comes out the other side through the culvert. The benefit with a culvert is that you can bury that if you need to get access to the work area. Here's another shot of the same site. Again, the trench box wall, and the water comes around. This is the culvert right here, the bypass culvert. I'm not sure you can see that real well, but I'm circling it, and it goes out into the stream. There's some erosion control protection too, so that it doesn't scour out the stream bank too bad. Here's just some other examples of impermeable barriers. We've got some steel sheeting being driven, sandbags. This one is not wrapped in plastic, but is doing a very good job. This is very turbid water. This is very clear, dark tannic water that's clear behind it. So there's also water bladders and a whole host of other impermeable barriers out there. We don't want to use dirt as a barrier. It's not impermeable, and we've seen them fail. So that's something that we would not recommend as a best management practice. Moving on with this diagram, now we've got our impermeable barriers in. The water is going to come from left to right again. It's going to come into an intake, and now we're going to talk about, instead of bypass culverts, we're going to talk about bypass pumping. So you're going to have some kind of intake, some kind of sump hole here, and a pump, and bring it around to the other side with some erosion control, energy dissipation on the other side. This could be a bypass. This could be bypass pumping, again, bypass culvert, bypass channel, if it's going to be a very long project. Again, we want to get to that, making sure that we're keeping the waterway completely fed during construction so that we don't dry anything up and we don't disturb too much of the stream while we're doing this construction. There will be temporary movement barriers with pumping and sometimes culverts, but again, we want to get that low flow, that Q2 that Dale talked about. We want to get that passed to keep the flow steady. Here's another diagram to go along with that. Your intake is in some kind of sump hole. I've seen these graveled. There's many ways to do it. I've seen a slitted barrel full of gravel where they put the intake. Many different ways to get this work done, but it's not on the bottom of the stream. It's off the bottom. And then you have your intake, usually a grate or something on here so you don't suck up wildlife or other critters. And it goes up and over that coffer barrier to the other side. Here's some real life examples from some projects that my staff have worked on in the past. Here's your intake. Here's your sump area. This one, they just had a fine mesh around it in a structure. And then here, the outlet doesn't necessarily have energy dissipation for this bypass culvert, but it does have erosion control protection. Some other bypass methods. Again, this is stream water, so it doesn't need to be treated. It just needs to be redirected during the construction project. That is a bypass culvert. This one they kept in place and put the new structure around this pipe. These are sheeting walls that kept the water going to the pipe. And because the pipe started to float a little when they took the material off, they used concrete bricks to hold down the culvert. There was no way to put in a bypass channel that didn't have a large potential of failure or a bypass culvert. So they kept the culvert in place and did this work with the existing pipe in place. And here's a bypass channel that was created. Lastly, dewatering the work area. So within the work area, this water is going to be turbid, and you're going to need to pump that out so that you can work in the dry most times. And again, a pump it out, put it into some kind of dewatering mechanism, and have some kind of secondary containment. Here's an example of that. Here's a sump with a pump, and the water is coming out on the downstream end of the project. This is a little unique situation here. These are dewatering wells. They're slotted points off of this tube, and they brought the groundwater down significantly in this area, and then the water was treated. Again, this is the dirty water that needs treatment. Here is a dewatering mechanism. This is a filter bag where the water goes to. That pumped water comes into here, goes through the pores. The larger sediment remains in the bag. And here's the secondary containment. In case this were to fail, you'd have a secondary containment before it went off toward the waterway. Just some other examples of different dewatering mechanisms. This is a steel baffle basin. This is a filtration basin with polymer to make the soil particles stick together and drop out quicker. And here's a filter bag basin. And then you're probably wondering, how do we get those materials into these structures? Well, it really depends on what you have for equipment, what you have for manpower, and what you have to get done. On the left-hand side is that buried slab span structure, and the material had to be brought in over the top. The only problem is that when you're pouring a top, when you're pouring that deck, you have the rebar that's sticking out from the sides that's got to join. So it makes it a little more difficult to get that material in. We had to have quite a bit of hand placement once it got down there to get that material in. And then this other structure, they had rented a small walk behind cat, for lack of a better term, with a little bucket, and were able to place and shape that material with rock bands and then the smaller fine material on top. Sometimes these fine materials need to be washed into the bigger rock so that you fill up all that pore space. And sometimes you'll need to use water to make that happen, which means that your dewatering system needs to be up and running to accommodate that extra water that'll be coming through the system. With that, I'm going to conclude here. Here's just another stream simulation through a crossing. With that, I'm going to conclude here and leave it for questions at the end. Thank you again for your time, your attention. I know we're talking a lot here, and I just appreciate being able to share this with you. Thank you very much.
Thank you, Bobby Joe. We're going to take another 10-minute break here before we jump into our last session and the closing Q&A. During this break here, I'm going to have a couple polls launched just to gather some information and see what interest brought you to this workshop. So if you could take the time to fill those out when they get released here momentarily, that'd be greatly appreciated. And we will see you back here for our last two sessions at 10:55. I just wanted to let everybody know that we are going to be stopping the first poll question right now and uploading our second one. Thanks for filling that first one out. All right, welcome back, everybody. We're going to jump into our closing couple of sessions here, and we're going to start with John Simonson with the Wisconsin DNR session on the importance of culvert inventories.
All right, thanks, Chris. Everything up on screen okay?
Yeah, everything's up and you look good to go.
Okay, perfect. Well, good morning, everyone. John Simonson with DNR here, broadcasting from beautiful Northwoods of Rhinelander, Wisconsin. I work with towns and counties and Wisconsin Department of Transportation on 4 counties up north, and then I also work statewide to help with stream connectivity issues, flood resiliency, and floodplain compliance as well. And today wanted to touch about the importance, when we're talking about all this stuff in terms of flood resiliency, culvert design methods, really wanted to touch on the importance of culvert inventory data and inventory efforts as an important piece of the puzzle here. So let me just get this to advance. Okay, so there's a lot that we shared so far, a lot of great information in terms of things to consider during design And, when we all go back to our, day jobs, so to speak, we're going to be faced with, when we're looking at these culverts, really, each one is a very specific combination of a whole host of factors and issues. It ranges from, what's the road surface like? Is it a problem site, or is it a site that looks pretty good? What does the watershed look like? All these factors. And I guess just to start, that's really to stress the importance of, there's a lot of, things we should be thinking about in this culvert design, but also really critical to this sort of work is working together, where you bring the expertise of the, road managers with, working with DNR or design consultants or whomever. So you can also look at, okay, what are the watershed characteristics? What are the stream characteristics? Because the more we can get those pieces to fit together, the better product we'll end up with in the end, both from the road and the stream perspective. But, over the years, obviously each site is unique, but, what I've seen over the years is generally what happens is most of these culvert projects, they really are scoped out site by site by site. A lot of times it's often when the culvert has failed or it's at close to the point of failure. And so with that, decisions often have to be made on a very short time frame. And there's also a lot of times not a lot of information about, well, what's the size of the watershed, or how long did that culvert exist? What was that lifespan of the culvert that was there previously? A lot of times not even that is known. So, without a lot of information available, that can lead really toward a heavy preference on decision making that's points to, okay, let's just put in, even if it's a problem site, let's put something in kind right now and we'll see if it gets us by for a few years. And then we'll see sites like this where right when you think you've seen every kind of road stream culvert situation, you'll get one that's definitely stands out. So taking a step back, it seems like most people agree with the concepts of, hey, it's a good thing to increase the size of culverts. It's good to think about flood resiliency, addressing maintenance issues. I think it's also really key, and we wouldn't be doing this issue justice if we didn't realize that there's also a lot of challenges out there. The transportation infrastructure funding is a very complex topic, right? And the reality of it is that there's county highway departments out there that are trying to get 70 years or more out of just maintaining the asphalt road surface. And that's even with Wisconsin winters, so, asphalt that should really realistically only be lasting 20 to 30 years. So, with that backdrop, I just want to say from DNR's perspective, I've learned a lot about, working with road managers and have a lot of respect for everything that goes into maintaining our public highways. And I get it, right? It's easy to understand with this concept, context and limited funding, time and resources, how it can be, difficult to approve in an investment in improving a problematic stream culvert. So hold that thought for a second, and starting to touch on culvert inventory. Pretty basic concept, right? A culvert inventory is you're basically gathering information at each road crossing, giving it an ID, recording some information, putting it up on a map, right? It's pretty interesting in Wisconsin. Statewide, we have a pretty comprehensive database that looks at road surface condition, the Whistler database, and we have a comprehensive bridge inventory as well, the highway structures information database. But statewide, we currently have a very limited picture about the condition of our road stream culverts statewide. And, we've seen the problems that can be caused when those fail. And in a lot of ways, this lack of information is, really ignoring the heart of our transportation system in some ways. So, and here's the bottom line too. If I could snap my fingers and tomorrow transportation budgets were doubled, right? I can't do that. But let's say there still would not be enough time or resources to make everything perfect within a year or two. So I think that context is exactly why culvert inventory data is so crucial. What that does is it puts us in a position where, we break that cycle of just short-term decision making site by site by site. Culvert inventories help us take a step back, and we know where the most flood-prone sites are, where the most sites that are requiring the highest maintenance costs, and where the high impact sites are, whether that's detour routes or with the environmental water quality aspect. So again, having that bigger picture, road stream culvert inventory is really key to let us take the next step so we can make strategic improvements over time and then make progress towards system-wide benefits. And that's both from the roads perspective and the stream and environmental perspective. They really do go hand in hand on this issue. Another, I think, really key aspect of why culvert inventory data is so key and so important. We all know that, and we've experienced this, especially over the last decade, given the amount of extreme precipitation and flooding events that we've seen in Wisconsin. We all know floods are very unremorseful, as I say, to revealing where the weak spots are in the transportation infrastructure. It's going to take its toll on the areas where the culverts are very undersized or where they haven't been able to be replaced quickly enough. And I think it's important. I think we all know, and we would all agree that having a tool so that we're able to address flood-prone sites before they fail, that saves us a significant amount of time. Avoids significant economic impacts, also avoids a lot of environmental impacts of what happens when these roads fail during flood events. So again, simply enough, inventory can help us identify those highest priority flood-prone sites. And I think Dale did an excellent job talking about this too. It's really important when we're talking about these road culvert crossings is to take that, kind of long range view. So you think about culverts, a culvert replacement cost, it's not just the cost of the culvert that's there, or maybe the replacement culvert, or if it's larger, a significant cost of those projects too deal with mobilization, setting up detour routes, excavation, all those other parameters that add a lot to project costs. So the more that we can install culverts that are lasting longer, we know the materials to use in terms of something that won't corrode over a longer lifespan. But instead of replacing culverts every 20, 30 years, if we can stretch that out into 75 years or more, that's where we can start to realize some direct cost savings to investing in these improved culvert projects. And so again, if you just look at the probability, if you want a culvert to last on the landscape that long, just looking at the, statistics behind what a 100-year event is, if we even know what a 100-year event is anymore, that culvert that we install, if it's going to last a long time, it's going to more than likely have to weather some significant flood events. And then, you overlay that with, what people are predicting in terms of, again, it definitely seems like we've experienced a lot of extreme precipitation events over the last decade. When you look at kind of the climate change perspective and the different modeling and what the experts are predicting for us in the future in the Midwest and in Wisconsin, increased storm intensity and frequency is going to, keep coming up against our transportation infrastructure. So it's something that we need to be thinking about now and planning for as best we can. And so again, thinking about, the benefits of culvert inventory, again, one of the real key things is, and this is something else I think Dale did a really good job covering, is we know that there's certain areas, certain watersheds that are a lot more flood prone than others. Dale covered this, it relates to gradient, soil, water infiltration, wetland storage, et cetera. But a culvert inventory, the benefit of that is we can look at the subset of culverts in these flood prone areas and then start, maybe emphasizing this is where we want to focus flood resiliency efforts. And to give a quick mention, there's some really neat stuff going on in Wisconsin right now. Ashland County Emergency Management and Ashland County Land Conservation Department are partnering with Wisconsin Wetlands Association, DNR, and many others. But they're implementing a project where they're looking at using natural flood management practices to help protect road infrastructure. So in this pilot project that's going on in Ashland right now, a road stream culvert inventory is really important because we want to look at where there's vulnerable transportation infrastructure, and that can help cite some of these natural flood management practices. So then you get the wide range of benefits in terms of wetland restoration, but also protecting the infrastructure as well. So there's a link on this slide if people want to look more into that project. So another aspect of why culvert inventory is so important, sometimes we talk about this and it can seem overwhelming, and it can be a very natural response to say, well, we're never going to have enough time, we're never going to have enough money. Culvert inventory data really helps us put this issue into perspective. We have to remember, not all sites out there are significant problems. In fact, many of them aren't. You can make minor adjustments, say to size or alignment or elevation, and those can have significant benefits on the flood capacity, resiliency of the culvert, but those can be pretty cost effective. But again, when we talk about 80,000 culverts on the landscape and talking about how are we going to fund these culverts, that sounds pretty daunting, but we can start to break this issue down where we can say, okay, 10 to 20%, those are our most significant problems, or we can break it down by road management level. I mean, we have to remember in Wisconsin, by far, most of the bridges and road stream crossings are managed by townships. So if you look at just intersecting the 24K hydro with the roads layer in Wisconsin, again, you got to be careful with averages, but the average township in Wisconsin has about 25 road stream crossings. So that sounds like a much smaller, much more feasible piece to start to break down, work with the town and say, okay, what are your top 1 or 2 priorities? Let's come up with a long range plan in terms of how to improve those sites. And again, culvert inventory can really be key to helping open up opportunities for cost share. There's a lot of resource agencies out there that really see the high, basically, return on investment when helping to cost share culvert inventory projects and road stream restoration projects. So, for example, if you go on the DNR website under the funding tab, you'll see some summaries of different cost share options that are available. And again, it's pretty powerful stuff when you go and apply for cost share. If you say, well, we know there's a problem site here. Okay, that might be a compelling story, but it's a lot more competitive if you say, well, we know out of all the crossings in our township or county or watershed, this is our top priority. I can tell you that goes a long way in terms of making it competitive for funding. And again, a culvert inventory can really open up a lot of funding opportunities. And it seems like even at the level of FEMA and thinking of flood resiliency, it looks like there's going to be a lot of opportunities in the future in terms of using culvert inventory data to make sites eligible for FEMA flood mitigation funding. So in other words, funding to improve the site before it's damaged in a flood. And the way FEMA thinks really key is they look at cost benefit analysis. And again, a lot of that can be integrated with road stream crossing inventory efforts to open up that funding, which really seems like it's going to become more available in the future. Another really important topic in terms of the benefits of a culvert inventory, it's efficient coordination, right? One is as simple as, staff changes over time, right? So then there's that transfer of knowledge at a culvert site in terms of what the past maintenance needs have been, how long that culvert has been there. Another real key benefit of inventories is it can really help when there's emergency flood response, both from mapping where sites are closed to, especially if it's something on the scale of a federal declaration, as you'll see in this news article on the right on the slide, when FEMA's involved, there's a lot of documentation, there's a lot that goes into that to be eligible for public assistance funding. If you have a culvert inventory already, then preloaded, you have the pre-existing conditions as they were before the flood occurred. That's huge in the way that FEMA looks at sites. So big benefit, as well as just coordinating with DNR or other agencies, because every site is going to have an IDs and a map. So you say, sites A, B, and C, these are the ones we're working on. So this is a broader kind of picture of really the power and the benefit of starting to implement culvert inventories on the landscape. Again, it's as simple as, it just helps encourage informed decision making. Again, transportation infrastructure, it's complex. It's at a whole lot of levels, ranging from a town board up to Federal Highway Administration. So the more, if there's not data available, a lot of people just assume the money isn't being spent the way it should be, right? Or they have an opinion. So if you have that culvert inventory data to say, listen, we chose to spend money to improve these sites as opposed to these, and this is why, and this is how it was prioritized, that can go a long way just in terms of making the case in terms of where funds are needed, or just making the case in terms of why funds were spent at particular sites. So touch real quick on culvert inventory methods. Again, this involves more than just going to a site and measuring the culvert dimensions and maybe the culvert condition. So it's really important to look at some key factors that help hone in on, okay, how flood prone is this site currently? What are the maintenance needs at this site currently? So it's incorporating things like, well, what's the integrity of the road core? How much fill is over the culvert? Is it a site where there's a lot of woody debris and sediment being transported that's continually blocking the culverts? And again, it's getting that picture in terms of how much are the road and stream fighting against each other. The more you can get those in line with each other, the more flood resilient it's going to be. And there's some good methods out there in terms of a culvert inventory to quickly look at some of the key factors that should be considered when you're recording that data on a site. This is for take-home reference. If you're interested in culvert inventory, I would love to have a training specific on inventory methods in the future. DNR and many others are partnering with Michigan DNR, and they've come up with some great culvert inventory methods. I encourage you to check that out. It's in an ArcHub environment, so you get the mapping that's publicly available. You can collect data on the phone. It's a great resource in terms of carrying out culvert inventories. And some more take home, there's some great work going on in Wisconsin, kind of recognizing the importance of culvert inventory data. The Wisconsin State Cartographer's Office is working on basically like a culvert inventory community of practice. These are people that are, incredibly smart with geospatial databases, and they're trying to put the pieces together so that, even though different stakeholders might record slightly different information, the geodatabase they're working on is going to be able to incorporate all that data into a single kind of clearinghouse, so to speak. There's also some great work, and this is going on out of the Northwest Regional Planning Commission. And again, they're doing some really neat stuff looking at, okay, if we assume that this culvert point fails, they're coming up with a method to look at, okay, what's the economic impact of that failure? And that gets into things like, daily traffic, detour routes, but just some exciting things that'll help us look at, okay, how do we look at the economic impact? How do we feed that into a FEMA cost benefit analysis? A great way to intersect that with the road stream crossing inventories. And a bunch of stuff going on with Wisconsin DOT, US Forest Service, county highway departments. So there's a lot of neat things going on in Wisconsin regarding culvert inventories. If you have more questions or want more information about the work that any of these groups are doing, feel free to reach out. And I definitely wanted to highlight, again, with this issue, it's a big, complex issue, and we're talking about road stream crossings, transportation infrastructure, climate change, flood resiliency. Partnerships are key in terms of doing the best we can to move forward. And I just really wanted to give a shout out today to all the great work that Trout Unlimited has done, and Land+Water and my friends in county conservation departments and DATCAP. the efforts that you've supported for culvert inventory and stream connectivity culvert replacement projects has been huge up in my area of the Northwoods. So that's much appreciated. And I appreciate all the work that went into hosting today's event. And with that, again, just wanted to thank everyone for their time and attention today. Reach out at any time for any questions or ideas. And with that, thank you very much.
Thank you, John. All right. And then our last session of the day, I'll handle this. We're going to be talking about an overview of partnerships and funding related to road stream crossings. A more formal introduction. I am Trout Unlimited's stream restoration manager for Northern Wisconsin. So I lead all of our efforts on stream restoration and culvert replacement projects. So this presentation is going to be slightly framed from TU's perspective, but I try to get a general overview of what partnerships can help you with and who those partners can be, and then talk about a variety of funding sources for projects, looking at different ways we might focus on those projects, be it flood resiliency, fish passage, or even from a planning perspective. So first off, I want to talk about partnerships. Here's just kind of a slide of some partners that Trout Unlimited and some of our partners have worked with throughout Wisconsin and the larger Great Lakes Basin and the eastern half of the United States even, being the U.S. Forest Service, Wisconsin DNR, and state DNRs in general, nonprofits like the Wisconsin Wetland Association, U.S. Fish and Wildlife Service has a lot of programming and technical assistance with these types of projects, Wisconsin Land+Water and associated county land and water conservation districts, the Wisconsin Department of Agriculture, Trade, and Consumer Protection, Wisconsin Emergency Management, Wisconsin DOT, and then FEMA. All of these partners have a variety of interests, whether it's flood resiliency or a more ecological stream health based focus. And, partnering with them can go anywhere from helping on planning, design, and implementation to providing cost share and funding opportunities. So I'll dive a little more into what partners out there are out there and what they might be able to help you with. The first thing I want to focus on are this broader partnership that's hosting this workshop today is our regional training efforts. And that's meant to start these discussions and give you the tools to start looking at projects. In our partnership, we do that a lot through project tours, where we look at sites that are exhibiting problems to give an idea of what those look like in the field, and then look at culverts that have been replaced to address those problems. We also host 2-day technical workshops that are kind of a drawn out version of this, where we're able to dive into a little more detail on design techniques. And then also go into the field and look at some survey and design techniques and how those, instead of just talking about it in a lecture setting, actually get in the stream and take a look at how those are completed. Another thing partners can help you with are inventories and prioritization. I think the one biggest takeaway we'd like to send you home with today is the importance of prioritization. It's much easier to deal with these problems at crossings if you plan for it. You're never going to avoid disaster striking, but mitigating that and doing inventories and prioritization are a good way of doing that. And partners can help from anywhere from helping to train your staff on how to complete these yourself, or even if you reach out to a partner like Trout Unlimited, we can go out and complete inventories for you and then supply you with the data that shows where problem crossings exist and where you might want to allocate your resources in the future. Another big thing partners can help with is survey and design work. This is often the technically heavy and can be kind of a bottleneck side or part of these projects, where getting this work done is the difference between saying, we know we have a problem, and then going to a funder or to your local government and saying, here's how we solve the problem. Organizations like Trout Unlimited can jump in and complete survey work. And in TU's position, we can complete at least preliminary designs. We don't have engineers or the permission from our board to complete full stamp designs, but we can get you there with a preliminary design and a cost estimate. So you can go to a funder and say, we need to finalize these designs, but this is what we want to do. Or you can have a preliminary design on the shelf so that if disaster does strike, what you can look at for alternative structures to avoid that in the future, rather than just replacing with what was already there. Grant writing, administration, and project cost share is another area partners can help with. This can often be a heavy lift with so many grant opportunities out there, just knowing what to apply to, but then also knowing how to apply or how to frame those applications to be competitive. That's where a partner can come in and help write these proposals and then administer the proposals, or honestly take the lead on it. That's where TU is able to help a lot of local towns throughout northern Wisconsin, smaller rural communities that might not have the staff on board or the experience managing complex state, federal, or private grants. We can come in and help administer those and work on joint priority projects together. And then in some cases where priorities overlap really well, organizations might have funding in pocket already to help cost share culvert implementation. Contracting and construction management. Once we get funding acquired and designs finalized, this is the next step, is executing a contract with who's going to be doing the construction, and then overseeing that construction to make sure the design plans and permits are followed. This is another area where if you don't have the experience managing this, the legalese of this process, where organizations like TU can come in and help carry that weight and do the construction oversight. And the last partnership opportunity I want to touch on is post-construction monitoring. Oftentimes when you're using grant funding, some sort of monitoring is required to show, did you accomplish the goals that our funding commitment was supposed to result in? And that's where, groups like the DNR or U.S. Fish and Wildlife Service doing electrofishing surveys for fish passage, if that's a metric you're looking at, can be helpful. Or even bringing in a group like TU or another watershed group of people trained in the Great Lakes inventory method can complete a post-construction inventory that shows what the inventory score for flood risk and fish passage are post-construction. And then you can contrast that with the initial inventory. So it gives you that nice snapshot on how have things changed based on this inventory method. This is kind of a quick overview of what some partnership or what partnerships can provide in some cases. It's not an all-inclusive list, and each partner is going to be able to provide more or less. Just speaking from Trout Unlimited, we've been in projects where we assist on one of these areas I've talked about. We've been on ones where we do all of it. So it's just a variety of looking at how much of a crossover the project is for our partners' priorities, and then also Trout Unlimited's priorities. And also just what the actual need from a partner is. Some don't need a lot of help. Some could use a lot more help. Next thing I'm going to talk about is a quick overview of funding. And I've kind of broken this down into funding categories based on what the project's attempting to accomplish. And I wanted to start out with project planning. This can kind of be a difficult area to get funding. A lot of time funders want on the ground projects and don't fund a lot of planning. TU has taken a tact of when we apply for larger grants to do implementation, we also include a small allotment to do future monitoring so they can continue that effort. But I do want to highlight one funding source from the state of Wisconsin. Their surface water grants program has a planning program, which we've had partners at various county governments apply for that funding to do inventories and survey and design work to identify the problems and start developing strategies to implement them. Another way to look at project planning is if you go to a funder with a preliminary design. So let's say you've reached out to TU and got a survey completed and a 30% design. You can then potentially go to a funder and say, I'm applying for both funding to finish this design work and then implement this design. So that's a way to kind of bring the two together. Aquatic organism passage, obviously, we've talked about it a lot today, is a big ticket item when we're talking about culvert projects, and a lot of natural resource funding agencies, nonprofits, and private foundations focused on the environment care a lot about this. So there's a lot of programs from a variety of funding sources. Some examples are the National Fish and Wildlife Foundation focuses a lot on this through their Sustain Our Great Lakes and Bring Back the Natives programs. U.S. Fish and Wildlife Service has the National Fish Passage Program and the National Fish Habitat Partnership. As I mentioned before, the Wisconsin DNR, there's the Surface Water Restoration Grant Program. We use that a lot in the state for our aquatic organism passage projects. And then groups like the National Forest Foundation, the Trout and Salmon Foundation, and even Trout Unlimited can provide some funding in cases for projects that are going to result in benefits to aquatic organism passage. Next up is looking at aquatic habitat. We've talked a lot today about how replacing undersized structures can actually just have a large benefit to overall hydrology in the stream, and that can result in improved habitat. Just looking at these photos here, the one on the left is where a road was actually abandoned. It wasn't used much anymore, and it was determined that we could actually just remove this culvert. So 5 pipes were pulled out of the stream here, and it allowed the stream to get rid of that flood and aquatic organism passage risk and just go to a natural channel. On the right is a structure that was replaced. It was 3 undersized pipes that were replaced with a single span structure. So that took away a lot of flood resiliency risks and also allowed the sediment to settle out and form a stream bed, whereas before it was just steel pipes and no structure in them. Funding for these can be very similar to what we just talked about with aquatic organism passage. A lot of natural resource groups like the National Fish and Wildlife Foundation, Trout and Salmon Foundation, Wisconsin DNR, U.S. Fish and Wildlife Service, and even private foundations really focus on this work. And a lot of times you'll see projects that are addressing aquatic organism passage can also be pitched as an aquatic habitat project. And finally, I want to talk about flood resiliency and infrastructure. This is really an emerging way for groups like Trout Unlimited that we're approaching projects. There's a lot of hazard resiliency programming out there from groups like FEMA, Wisconsin Emergency Management, Departments of Transportations, and even some groups like the National Fish and Wildlife Foundation. They have a resilient communities program. And a lot of this is focused on finding ways to address the emerging climate crisis and increasing flood issues we're seeing across Wisconsin, the Great Lakes, and the United States as a whole, with solutions from both natural infrastructure, like putting in wetlands or restoring wetlands, and then our gray or built infrastructure like road stream crossings. So there's a lot of these programs out there that if you can show we have repeated flood damage or risk of flood damage at a site, it's a way to unlock a significant amount of funding from these programs. Just speaking about FEMA as a whole, they had hundreds of millions of dollars just this past year for projects like this. So it's an emerging area that has a lot of opportunities. They're complex, they're new, they can be difficult to navigate, but that's where partnerships plug back in. Like I said, with grant funding and cost share, we're working with Forest County on a FEMA proposal right now to their new Building Resilient Infrastructures and Communities program. It's a brand new program. It's growing up and we're trying to figure out how it works. And working as a partnership has allowed us to do that, whereas going it alone might have yielded different results. One last thing I want to say about funding before kind of closing this part of the presentation is a lot of times these projects have more than one benefit they're going to have. You'll often see benefits to aquatic organism passage and aquatic habitat and flood resiliency. You might have your reason for prioritizing a project, and that might be the area you want to go. So if you're saying this is a flood resiliency project, I'm going to apply to FEMA for this. But don't forget to hit on those other benefits, because that can take you from being just another flood resiliency project to a much more competitive project, because you're looking at how this is going to benefit the entire system. Last thing I want to advertise is upcoming events and trainings. Like I mentioned earlier with our regional trainings, we really like to get out and show people how to do this work. The partnerships are key. These projects are much easier in partners, but we want to give you the tools to at least start them or even lead a project on your own. We had to cancel our events last year, obviously, because of the pandemic, and we're hoping that we're able to return to in-person events later this year. So in preparation for that, and we'll try to keep everybody on who had registered for this workshop updated on when these events are going to be, is we're hoping to have a crossing project tour in either summer or fall, and it's planned to happen in the Hayward area. We then hope to have one of our multi-day design workshops later in the fall, and that's going to be based in Ashland. Both of those are going to have field components. The road stream crossing project tour will be one day and be all field-based, checking out a number of sites. The crossing workshop will be both in-class lecture, kind of going over design techniques and kind of like what Dale was focusing on earlier. And then we'll go in the field to get some of that stuff in practice. And then one thing we're exploring about implementing once it's safe to be in groups again is offering road stream crossing inventory training sessions. And while this is called the Great Lakes Road Stream Crossing Inventory Method, it can be used across the region. It's very applicable and transferable. So if there's interest in learning how to use the inventory methods, reach out to us. And then we can, at the current, look at setting up small group stuff that we can do safely. And once the vaccine rollout is further along, we can look at hosting more formal, larger regional events to get people trained on the inventory method. And with that, I'm going to close my part. I know I went pretty quick through there and there was a lot of information. That was kind of the nature of today, but we're going to jump into a question and answer period. I've been keeping track of questions asked so far, and I am going to go ahead and start reading through the ones we've received. Feel free to keep adding them into the chat. I think we're going to try to keep questions in the chat if people are okay with that. With just the number of people, I think it'll be difficult trying to ask questions out loud, but we'll answer these ones we have first. The first question asked was, does Trout Unlimited provide technical designs for their restoration projects? If not, which organizations complete technical designs? The answer to that is yes. We do provide designs for restoration projects, at least in the preliminary phase. In some cases, we have funding aside to hire a consultant to finish those. In other cases, we're working with a partner that once we get it to the preliminary, they take it and go get it finished. I see we have a hand raise. The name I have is Dylan's iPhone. So if you had a question you wanted to ask. All right, maybe not. I'll keep going here. The second question, and I'm gonna, as I read these out now, I'm gonna rely on my co-presenters here today to jump in when they think they have a good answer for it. So when you create better flow conditions for flooding events by upgrading the pipe size, is there cause for concern of downstream areas that will now bear the brunt of these storm events? I know this one was given a couple answers in the chat, where a lot of the times that risk is minimized just by improving flow, both allowing wetlands to act as kind of their natural sponge and slow the flow, but also the risk associated with a small or an improperly designed structure is that if it fails, not only do you get that flow event, but also all the debris and road material and the structure itself heading downstream. But Dale, do you have anything you want to add to that?
Well, I'll add a couple of things. One, it seems more of a concern in urban areas. I've very limited experience there, but I would say two things. Well, it depends on kind of the storage capacity upstream. So if you're building up a big head, how much storage capacity is there? Are you really storing enough to really decrease the flood peak or not? So that's kind of a site-by-site situation. But the other thing is keep thinking, if we want these structures, to last 50, 75, 100 years, and a lot of times they're replaced because either they failed or they're in poor condition. That's your one chance to restore the system. So if you don't take advantage of it and restore the channel morphology, the flows, fish passage, you may not be able to do it again for another 75 years. So it's just a matter of balancing those out, knowing what's downstream. And I think it gets back to some of the floodplain zoning issues and that sort of thing, but it's sort of a site by site, but I would really argue to try to restore if you can. So thanks.
And I'll just jump in again. When we look at these projects, if we have several crossings in close proximity, we try to look at them all to see, are they all undersized and going to have problems, or is it just one to where we think, it's just that one culvert's the problem? If we identify other ones, we might start working our way from downstream to the upstream area so we aren't overloading a succession of culverts. But a lot of times what we find is that, like John said, a lot of culverts actually aren't exhibiting major problems, and you might just need to find that one. But I would say before working on projects, if you have concerns downstream, take stock of what's downstream and how it's performing. Because if there's the same problems there, you might want to look at maybe starting from the downstream and working your way up. All right. Our next question I have is, where I fish in northern Wisconsin, it seems like new work is a blend of traditional bridges and then ecological culvert designs. How do you decide when to use an ecological culvert design versus a bridge?
You want me to take a crack at that first? So a lot of that I think gets back to the question of more the road and road management objectives. We talked about ecological culvert design. Lots of structures will work. So it probably comes back to the size of the stream. Can you accomplish your objectives with say a pipe arch culvert, because that's going to be cheaper? And then does that meet the road management objectives? And then as the stream gets bigger, then that pushes you to bigger structures and then ultimately to a bridge. But that's got to be sort of balanced as much with the safety and the road. The road's there for transportation, so you got to meet all those objectives too. So it's a matter of balancing those out. The bigger the stream, then you gradually migrate up to a bridge. One thing I'll say in some of my work with civil engineers, I know that sometimes they would prefer a box culvert or something like that before they get to a bridge, just because they don't fail the same way and the inspection standards aren't quite as great. So I think there's some practical engineering road management considerations built into that, but it's a matter of balancing all that out with costs.
Thanks, Dale. Anybody else have something they want to add to that, or you think we're good to move along? All right. Our next question is, has anyone noticed any differences to beavers trying to dam up water at different types of culverts? Or if a culvert where there was existing beaver issues that has been replaced, is there a noted difference in beaver activities based on that replacing design? Just speaking from what I've learned, I know beavers can be a contentious topic, but a lot of times the issues we see are the fact that undersized culverts kind of create that trickling sound that draw beaver in, and the fact that they're undersized, it's much easier for them to construct a dam that blocks the whole culvert. So what we've seen in some sites we've worked on is that a lot of times going up to that single span structure, just using one bankful size structure, creates an environment where beaver can't dam it as easily and aren't as drawn to the site. In the event where we're working on smaller streams where we still keep a pretty small structure, we've actually used mitered culverts where the inlet is actually cut at an angle so that if beaver do build a dam, water can flow up and over the dam and still get into the structure. So basically that beaver construction isn't plugging the entire inlet. Dale, John, Bobby, or Maureen, have anything else you want to add to that? I know it's a complex issue.
No, I think you covered that. Oh, go ahead, Dale.
I think you hit the nail on the head by going to a bankful with structure set lower. It's not as attractive as these undersized culverts are. So that helps reduce the problem. It's harder for them to plug in. And certainly you talk about a beveled or a step bevel culvert, makes a big difference just for handling the flows and being able to clean out and not damage the culvert. And I think that's been, there might be some people here from the Forest Service, but I think that's been the general experience on the National Forest, that by installing those bankful width culverts, the problems have declined quite a bit. They don't go away completely, but it really minimizes them.
Do you have something you wanted to add, John?
No, I think you both covered it very well. There's no such thing as a beaver-proof culvert, but the better you can get a single structure for sizing, so it's less attractive and easier to remove the debris, the better.
My name is John Christensen. I've worked with Dale in the past on a lot of these stream crossings, and I've noticed that with the beaver dam issues, that I'm primarily the equipment operator and equipment operator work leader, and find that the step bevel culverts that we put in, if there has been a problem with beavers, you can get in there and clean them out a whole lot easier with an excavator and get them cleaned out. And if you have to resort to getting the beavers trapped out of there, you can continue to clean them out while there's beaver activity and keep the structure intact versus doing damage to the structure or anything like that with a flush mount style culvert.
Thanks, John. Next question we have is from a land conservancy in Wisconsin, the Mississippi Valley Conservancy, where their nature preserves have trails and access lanes that use open fords as their road stream crossings. They're wondering, in what scenarios are ford crossings more resilient or practical? And could you touch on when a ford crossing or culvert crossing would be a better option?
You want me to take a crack at that? So my first response is, well, I have a lot of site-specific questions, but so I know the question was for the southwest part of the state. So I know they have, pretty flashy flood flows, maybe not as many wetlands, hard bottom, streams, but I also have a lot of question about it. It sounded like a lot of it was trails. So the actual type of crossing makes a big difference. Are we talking, foot traffic? Are we talking bike trails, ATV trails, or actual vehicle roads? And that all would make some difference. In a lot of parts of Wisconsin, I'm not a big fan of fords, but we have so much wetland, organics in our wetlands, soft bottom streams. But if you have a hard bottom stream with, really sort of flashy flood flows, I've seen some cases where fords can work, especially if you don't have a lot of traffic and it's carrying a lot of dirt and mud into the stream. And they're obviously cheap. You can construct if you have a good hard bottom, but you sometimes need to do some construction. So you want to harden the approaches. One thing I've seen though is like sometimes there are concrete pads poured and that they can become a barrier to fish. So if you can design it in a way so it's hardened but maintain some kind of a low flow channel, they can work. And I think especially for for areas where there isn't a lot of vehicle use, they can function okay, but just depends on the specifics.
Thanks, Dale. Our next question, and this might go to multiple people that presented today. When installing a 3x5 foot or 4x6 foot pipe arch, are you installing rocks and substrate into the culvert, or are you allowing that to happen naturally? And I'll kick it off by saying that depends, and then dump that off onto our co-presenters.
I can start that one. This is Bobby Joe. So a lot of it depends. But we go with a rule of thumb as an agency when we're reviewing the designs that come in, that if the stream is 1% gradient or less, we try to set and we've got the material recruitment upstream, and I'll get into what that means in a minute. We don't typically put material in the bottom of a structure unless there's outstanding circumstances. So if there's material built up, aggregated upstream that we would like to mobilize to maybe expose some spawning redds, or it just needs to be mobilized like it naturally would through the stream corridor, then we typically are not putting material in the bottom of them. Again, there's always outstanding circumstances. If we want to have a low flow channel, we might be putting material in. And when we have small culverts, like the ones identified, what we've typically done, or what I've seen in construction, is that they come in segments, and then we put material in one segment, attach it to the next segment, put material in that segment, and so on and so forth, as well as you can, because they're so tiny. So I've had a few of those over the years that I've seen where we did put material in. Not common though. And usually when your streams get to be 1% gradient or higher, that's when we start putting in material. And then we make sure there's space for that material, and the construction methods depend on what structure is chosen. That's my first my first brush on that. If anybody else wants to add anything.
Well, I think that's a good overview, Bobby Joe. And I'll just add, so sometimes the why behind it is, when we get into those higher gradient streams, the stream itself is going to have coarser substrate, gravel, cobble, boulders. But two, if you set a pipe at like a 2% slope, and if there's no like roughness on the bottom, that water is going to shoot through there very high velocities, make it so fish can't pass. So if you design a bed through the structure, I mean, that can protect your footings, protect from scour, but also add that roughness to the bottom where, you still get that aquatic organism passage up through the pipe.
Yeah, and this, Dale, I'd add to that, think back to this very low gradient versus something higher than that. Like John said, at some point you have to build a bed through to get fish through, but also to if you want the flood resiliency and you want the abrasion resistance, but the structure's got to be bankful with. So, the question was about like a 5x3 or 6x4 pipe arch. Those are pretty small streams. And my comment there is that would only work on these more than, in most cases, very low gradient streams where it's a sand bed, it's only moving sand, and it's a narrow stream. So you're thinking a bankful width of 5 or 6 feet, and where you can put in that culvert, set lower, pass your flood flows, allow a natural bed to move through there. Now it is possible. There are a few cases where, sometimes you can crawl in and hand place a few rocks if you want to provide a little diversity in there. And even, getting into a 5x3, that's pretty, it's hard to get in there. So if you have a higher gradient stream, it's moving gravel bed load, like John mentioned, you have to build a bed through there. So you need room for your bankful channel, plus, bank rocks. And if you're inside a pipe arch, it's got to be bigger than that. I think the smallest one we worked in was, you had to duck down to get into it. So it was about 5 feet high, probably 7 feet wide. And even that, it's hard to move material in. We could just barely get one of those walk behind front end loaders in there to build the material bed in there. So you're kind of limited that way. If you need to build that bed through there, there's kind of a minimum practical size. So I hope that helps things.
Well, thanks for that, everybody. Next question, I think, is going to go right to Dale again. How does the headwater to depth ratio for ecological culvert designs compare to traditional designs? Are there references for Manning's end values when filling culverts with materials? And are those references as extensive as shown in the example pictures you had, Dale?
So I'll go ahead and start with the headwater to the depth ratio. So like some agencies, maybe a lot of these townships, they may not have standards or not. Some of the other agencies, whether they're federal or state, I showed a few examples in my presentation on traditional culvert design. So, a lot of those have a design discharge, and then they're allowing a headwater depth ratio of 1.1 or 1.5. And like I said, some cases it might even be up to almost the top of the road. So, it depends on the agency. If you're going to use stream simulation or ecological culvert design, we're saying we want to keep that culvert from seeing full pressurized flow. So the idea is to keep it to 0.8 or less, and then that provides some freeboard for your floods and also for debris passage. So, I hope that kind of clarifies that. And then the next question was end values. So there are two ways to approach it. If you're going to put material, either you're going to let like a natural sand bed move in, or you can build your bed through the culvert. You can use the same end values pretty much that you're going to use in your channel, upstream or downstream. So that's, depending on for like bank flow and flood flows, a lot of times you're in that 0.035 to 0.5 or 0.06, 0.05, 0.06. And then in terms of your hydraulic modeling, there are two approaches you can use. If, like sometimes for the bank full width culvert on very low gradient streams, or you set it lower, we'll estimate how that might fill with, with a sand bed. And then you can actually in HEC-RAS, if you're going to HEC-RAS the culvert module when you're putting in, you can block the bottom. So if you think it's going to fill to a foot, you can block that. And then you can also, have an option to put in an end value for the bottom and that distance, and then an end value for the top. So the top would normally be what you do for the culvert, which would be a lower value, but then you can use, a little higher value for the bed, and then just match it to is it sand or is it gravel? Now, if you're doing full, building a bed and the banks through there, the other way you do that in HEC-RAS is if you want to model and be able to do your sediment mobility and stability, you can use an option in HEC-RAS where you don't put in a culvert, you put in your cross sections for your channel, and then you put a lid over the top that mirrors the structure that you're going to put on top of it. The same thing, you use one end value for your cross section, another one for the lids. That's how you would handle that. So thanks.
Thank you, Dale. Our next question is, looking at land use in the area of a site important to consider when trying to understand the behavior and output of a stream during a flood event?
I'll take a quick jump at that. Absolutely. Whether it's forestry operations, stream degradation, head cuts, urbanization, size, type, shape of the watershed. Yeah, definitely really important to look at as we, look at project designs or maybe why problems are occurring and what some of the solutions are.
Something TU is looking at as we're partnering on some projects with groups like the Wisconsin Wetlands Association is also tied into this with what's our wetland system like upstream and around a culvert? Is it fully functioning or has it been highly modified for some other sort of land use, be it urbanization or agricultural use? And that gives us an idea of what sort of retention we're going to have during flood events. And, then also gives us an idea like, should we combine some sort of wetland restoration project with a culvert project to increase our benefit? So yeah, taking a look at that is incredibly important because it could vary greatly if you're working on a stream, let's say a 10-foot bankful stream in a heavily forested, largely intact, portion of the Chequamegon-Nicolet National Forest versus somewhere, let's say in the southwest part of the state where you have a similar stream gradient, similar stream size, but you're surrounded by modified land for residential or agricultural use. So lots of variability there between streams that could look pretty similar, at least in terms of their size and flow gradient.
Yeah, and just to add, we weren't able to touch on this today, but I mean, there's areas in the state where, especially in urban areas, where the discharge, for capacity, there's structures in much greater than bankful width. So the design actually incorporates low flow channels to reduce the span so that the water doesn't spread out and get, super shallow.
Yeah, and thanks for bringing that up, John. Like John said, we haven't had the chance to talk about that in too much depth today. But these low flow channels are when we have to kind of supersize structures to handle highly modified and flashy flood or discharge events. That's designed so that when we are at base flows or below base flow, we don't have a super shallow channel that then can't support fish because the channel itself is just too shallow and either gets too hot or isn't deep enough. Incorporating that low channel design allows us to both accommodate these exceptionally high flood events, but then still give the flow characteristics needed during our base flows.
And I've also run into whether or not it's a navigable stream or not, where they want to be able to have kayaks or canoes go through, and I've seen that in a couple of pictures in some of our presentations where they upsize the head wall of the culvert so that they can allow navigable passage through.
Yeah, thanks for bringing that up. That's been something we look at too when we are working on a project in an area that's highly used for recreational paddling. If we look at a crossing that's been a portage in the past, we look at, is it feasible to put a structure in here that you could paddle through? So keeping stuff like that in mind too can be good. And I'll jump back to funding because it's what I'm always thinking about. If you have an area like that, you can then look at public access and recreational funding as well to look at road stream crossing projects. Anybody else want to touch on land use? Okay. The next question, which areas of aquatic organism passage and stream simulation are most poorly understood? Where is the most potential for improving these types of projects, the structures used, or the design methods? Overall, what's next and that we see in the evolution of these types of projects?
Well, I can jump in with just one concept. I mean, sometimes when we talk about culverts and different design methods and different perspectives, it can be perceived as, well, it's just a DNR thing, concerned about fish passage. DNR, why don't you pay for it? Or it's just a highway issue. So I guess the biggest thing is, working on these issues over the years, time and time again, I see the broad benefits of coming together, cross-discipline, looking at it from a variety of perspectives. And again, it comes down to the simple fact that, well, whether we call it stream connectivity or stream simulation design or hydraulic design with a certain flood passage standard, it all comes down to the more that we can accommodate the expected range of flows, remembering that streams also pass sediment and woody debris. the more again, as simple as the more we can get the road and culvert to not fight against each other, the better it is from a broad range of perspectives. So I guess with that, sometimes we put a label on it like stream connectivity or ecological design. It gets people thinking in one direction quickly, where I think we're all better off if we look at it from that broad perspective.
You know, I'll maybe jump in there, you know, in terms of, I guess what I would say is sometimes people maybe don't appreciate the value of getting out to bankful width. So that's, I think, really important. And then the other two things are the importance of that stream profile survey, and basically being able to use that to understand, you know, what kind of sediment might be moving, and then also how the existing structure may have impacted the stream profile, and then so you can take that into account your new design. So those are maybe a few things I would point out.
I would also just add as a end note to that is, you know, we're continuing to see what future conditions are trending towards and looking at how our projects are accommodating those changing precipitation and flood events. We have good returns from some of the design methods you know, nothing's going to be a foolproof design, but you know, overall, the stream simulation ecological culvert design seems to be performing well, but just continuing to monitor and check on performance post-construction is key to helping inform what can we do differently in the future, what can we improve or tweak on a certain type of stream. Next question, what is the practical size, maximum size of a culvert before you'd want to shift to a bridge? This is kind of a follow-up to an earlier question. And then are multiple culverts still used, or is that poor design? I'll jump on that second question there. We avoid multiple culverts for the fact that while they can increase the amount of water you're passing, every culvert you add is just adding another area where you can hang up debris and create log jams. So we had already talked about beaver issues at undersized culverts. Even without beaver, we can have major issues with clogging, especially when using multiple pipes. It just creates a lot of hang up potential for woody debris and other stream debris that would have passed a single span structure. So we avoid those when we're looking at these types of projects.
So, and Chris, I'll jump in on the multiple culvert issue too. I would say absolutely, if there's any way possible, avoid multiple pipes for your bankful width and beyond channel. Some people talk about putting in floodplain relief culverts. So depending on your situation, I mean, I would prefer to go with more area under your single crossing. And if you got to build a wider banks or something like that, or the other option is at least get out to bankful width or a little bit beyond, then you may want to consider, if you absolutely need to, if you have say a lot of water being transmitted during your flood flows over the floodplain, then you could consider floodplain relief culverts at that time. You know, I pretty much, you know, after a little bit of experience, any projects I've run, tried to avoid multiple culverts. But there are a few cases where we've done it, and I had one of those flood examples I showed that survived the flood, the first floor. One of those actually has 2 culverts there, and the reason for that is it's on an alluvial fan. So it depends on your site-specific characteristics, which is a depositional feature where you have a main channel, but during overflow, it can flow into other channels. So that second culvert was to help catch overbank flows on that specific feature. They're not as common in northern Wisconsin. They're certainly around. You find them all the time in the mountains and other areas. So some of that gets back to site-specific characteristics, but for that, your main channel, boy, try to avoid multiple structures if you can.
And then
we ran into that on one of the culverts that we installed down south of Leona here, where we put in 2 culverts and we put them side by side, and it ended up where the channel stayed in the outside bend of that, and it ended up like a overflow situation instead of the stream using both culverts as a main flow. The channel created in one culvert and then created a alluvial fan in the other culvert. So it was only being able to use during a high flow situation. We've seen that on our field presentation last year's session.
Yeah, thanks for that. That is something we do see where sometimes we upsize and still use multiple culverts. You can kind of see a bank forming and cutting off one of those pipes. So it's only actually used during the high flow events and sometimes can't even access it then. Dale, just quickly, we're coming up on, we're just past noon. So I'm going to wrap this up, everybody. We really appreciative to have you for so long this morning. So I just want to touch on the last couple questions here. Just quickly, Dale, is there a practical maximum size for a culvert before you would just say use a bridge, not a culvert?
Well, I would probably defer more to the engineers and road managers. I see one person address that said 14 or 15 feet, but Wisconsin DOT has standards for three-sided box structures up to 42 feet. You can put in conspan structures, and some people will consider that a bridge, but it's not, technically a bridge. So anyway, you start getting anywhere from 15 out to 40 feet, but I would say some of those box culverts, you can have those out to 20, 25 or 30 feet, and then you pretty much get pushed to a bridge, but defer more to the structural engineers on that.
And then the last question we'll have time for was a question about looking at restoring upstream reaches, wetlands, floodplains, et cetera, to help with culvert design. And we haven't touched on that much today, unfortunately. It's just one of those things we couldn't fit in. But yes, when we look at systems that have been highly degraded and impacted outside of the structure, we do like to consider that, because that is just going to further help whatever structure we put in if we can restore some of that flood capacity. It's not always possible. It depends on, are you working on public or private land? And if you're on private land, you have willing landowners. But it is something to consider when looking at projects. That is there an opportunity upstream to restore some function, especially if that's really going to help with your system's flood resiliency. With that, presenters, any closing comments you want to make before we wrap up?
Thank you to everyone for their interest.
Yeah, thanks everyone very much.
All right. Thank you all so much for sticking around with us for so long today. Keep a look on your email later today or tomorrow. You should be getting one with an evaluation to help us kind of inform future outreach and activities we do. There will also be a copy of all the presentations we gave today on there for your records. And those all include our contact information. So feel free to reach out with questions or interest in exploring potential projects, training opportunities, et cetera. We really appreciate you joining us today and hope we were able to leave you with some good information. So thank you all so much and have a great rest of your day.